A cosmic leviathan, heavier than imagination, older than time itself, or so it seems. Out in the vast, cold dark, this black hole burns with impossible brilliance. A gravitational monster devouring everything in its reach, yet somehow illuminating secrets we were never meant to know. The light from TON-618 has traveled for over 10 billion years, yet calculations suggest it formed when the universe was still a newborn. It defies our models. It mocks our physics. TON-618 is a distant and extraordinary object in the universe, classified as a hyperluminous quasar. This cosmic powerhouse lies over 10 billion light-years away from Earth, making it one of the most remote and ancient objects we can observe. Quasars are incredibly bright celestial bodies powered by supermassive black holes at the centers of galaxies, and TON-618 stands out as a true giant among them. What makes TON-618 particularly remarkable is the sheer size of its central black hole. Astronomers estimate that this behemoth contains a mass equivalent to 66 billion suns, making it one of the most massive black holes ever discovered. To put this into perspective, it is about 10,000 times more massive than the black hole at the center of our Milky Way galaxy. The immense gravity of TON-618's black hole pulls in vast amounts of surrounding matter, creating a swirling disk of superheated gas and dust. As this material falls towards the black hole, it releases enormous amounts of energy across the electromagnetic spectrum, making TON-618 shine with the brightness of over 140 trillion suns. Studying objects like TON-618 helps scientists understand the formation and evolution of galaxies in the early universe. Its existence challenges our current models of black hole growth and raises questions about how such massive objects could form so quickly after the Big Bang. As we continue to observe and analyze TON-618, it may provide crucial insights into the nature of quasars and the role they play in shaping the cosmos. The supermassive black hole known as TON-618 was first identified in 1970. It was initially catalogued as a quasar, which is an extremely bright and distant active galactic nucleus. The discovery was made during a survey of celestial objects that emit strong radio waves and appeared bluish in color. At the time of its discovery, astronomers did not yet fully understand the nature of quasars or their relationship to supermassive black holes. It was only later, as our understanding of these cosmic phenomena evolved, that scientists realized TON-618 was powered by one of the most massive black holes ever observed. The true scale and significance of TON-618 would not be fully appreciated until decades after its initial discovery. As astronomical instruments and techniques improved, researchers were able to more accurately measure its properties and estimate the incredible mass of the black hole at its center. This discovery highlights how our understanding of the universe constantly evolves. Objects like TON-618, first spotted as curious bright spots in the sky, reveal themselves over time to be among the most extreme and fascinating phenomena in the cosmos. TON-618 is a distant and extraordinary object located in the constellation Canes Venatici, which translates to hunting dogs in Latin. This celestial behemoth resides in the northern sky, billions of light-years away from Earth. To put its immense distance into perspective, the light we observe from TON-618 today began its journey towards us when the universe was less than half its current age. This hyperluminous quasar stands out as one of the brightest objects in the known universe, outshining entire galaxies. Its extreme luminosity is powered by what is believed to be one of the most massive black holes ever discovered. The black hole at the heart of TON-618 is so enormous that it challenges our understanding of how such massive objects can form and grow in the cosmic timescales available since the Big Bang. Despite its vast distance, TON-618 has become a subject of intense study for astronomers and cosmologists. Its existence and properties provide valuable insights into the formation and evolution of supermassive black holes, the structure of the early universe, and the physical processes that occur in the most extreme environments in space. The discovery and ongoing observation of objects like TON-618 continue to expand our cosmic horizons, reminding us of the immense scale and complexity of the universe we inhabit. As our telescopes and detection methods improve, we may uncover even more distant and massive objects, further challenging our understanding of the cosmos. TON-618 is a hyperluminous quasar located in the constellation Canes Venatici. This cosmic giant lies at an immense distance from Earth, approximately 10 billion light-years away. To put this vast expanse into perspective, the light we observe from TON-618 today began its journey when the universe was less than 4 billion years old. At such an extreme distance, TON-618 serves as a cosmic time capsule, offering astronomers a glimpse into the early stages of galactic evolution. The quasar's incredible brightness allows it to be visible across this enormous gulf of space, making it a valuable subject for studying the distant universe. The extreme remoteness of TON-618 also highlights the incredible power of modern astronomical instruments. Our ability to detect and study objects at such vast distances showcases the remarkable progress in observational technology and our growing understanding of the cosmos. TON-618 stands out as a true giant among black holes, dwarfing even the largest known stellar black holes by an almost unimaginable margin. This ultramassive black hole sits at the center of a quasar more than 10 billion light-years away from Earth, making it not only one of the largest known black holes, but also one of the most distant we can observe. The sheer scale of TON-618 is its most striking feature. Scientists estimate its mass to be around 66 billion times that of our Sun. To put this into perspective, it is about 10,000 times more massive than the supermassive black hole at the center of our Milky Way galaxy, which itself is already millions of times the mass of a typical stellar black hole. Another unique aspect of TON-618 is the intense luminosity of its surrounding quasar. The material falling into this behemoth black hole creates a brilliant accretion disk, releasing enormous amounts of energy. This makes the quasar one of the most luminous objects in the known universe, outshining entire galaxies. The existence of such an enormous black hole so early in the universe's history also presents a puzzle for astronomers. It challenges our understanding of how these cosmic giants form and grow over time, prompting new questions about the conditions in the early universe that could have allowed for such rapid growth. TON-618 captivates astronomers and space enthusiasts alike due to its extraordinary nature. This distant quasar, located billions of light-years away from Earth, harbors one of the most massive black holes ever discovered. The sheer scale of this cosmic titan defies our understanding of how such enormous objects can form and exist in the universe. What truly sets TON-618 apart is the estimated mass of its central black hole. Scientists believe it could be as heavy as 66 billion times the mass of our Sun. This colossal size challenges our current models of black hole formation and growth, pushing the boundaries of our knowledge about the early universe and the evolution of galaxies. The extreme brightness of TON-618 also contributes to its mysterious allure. It outshines entire galaxies, making it visible across vast cosmic distances. This intense luminosity comes from the immense gravitational forces at play, causing surrounding matter to heat up and emit powerful radiation as it falls into the black hole. Furthermore, the existence of such a massive black hole so early in the universe's history raises intriguing questions about cosmic evolution. How did TON-618 grow to such an enormous size in a relatively short cosmic time frame? The answers to these questions could revolutionize our understanding of the universe and the forces that shape it, making TON-618 a subject of ongoing fascination and study for astronomers worldwide. TON-618 stands out as a true giant among black holes. This ultramassive black hole dwarfs even the largest supermassive black holes found at the centers of most galaxies. To put its size into perspective, TON-618 is estimated to have a mass of 66 billion times that of our Sun. This makes it one of the most massive black holes ever discovered. Compared to Sagittarius A star, the supermassive black hole at the center of our Milky Way galaxy, TON-618 is truly in a league of its own. Sagittarius A star has a mass of about 4 million solar masses, which means TON-618 is over 16,000 times more massive. Even when compared to other exceptionally large black holes, such as the one in the galaxy Messier 87, which was imaged by the Event Horizon Telescope, TON-618 still stands out. The Messier 87 black hole has a mass of about 6.5 billion solar masses, roughly 10 times less than TON-618. The sheer scale of TON-618 challenges our understanding of how black holes form and grow. Most supermassive black holes are thought to have grown over billions of years by consuming nearby gas, dust, and stars, and by merging with other black holes. However, the existence of such an enormous black hole so early in the universe's history raises questions about whether our current models of black hole formation and growth are complete. The discovery of black holes like TON-618 pushes the boundaries of our knowledge and forces us to reconsider the limits of what is possible in the cosmos. As we continue to explore the universe and uncover more of these cosmic giants, we may need to revise our theories about the formation and evolution of galaxies and their central black holes. At the heart of a distant quasar lies TON-618, a supermassive black hole of truly staggering proportions. Astronomers estimate its mass to be around 66 billion times that of our Sun. This colossal object is one of the most massive black holes ever discovered, dwarfing the black hole at the center of our own Milky Way galaxy by a factor of over 10,000. The sheer scale of TON-618 challenges our understanding of how such enormous black holes can form. Its immense gravitational pull affects everything around it, shaping the structure of its host galaxy and influencing the formation of stars and other cosmic bodies in its vicinity. Detecting and measuring such a massive object requires advanced observational techniques and careful analysis of its effects on surrounding matter. Scientists study the motion of gas and stars near the black hole, as well as the intense radiation emitted as matter falls into its gravitational grasp, to determine its extraordinary mass. The discovery of black holes like TON-618 pushes the boundaries of our knowledge about the universe and raises intriguing questions about the role these cosmic giants play in galactic evolution. As we continue to explore the cosmos, we may find even more massive black holes, further expanding our understanding of these enigmatic objects. TON-618 stands as a cosmic behemoth that pushes the boundaries of our understanding of black hole formation. This ultramassive black hole, located in a quasar more than 10 billion light-years away, is estimated to have a mass of 66 billion times that of our Sun. Its sheer size presents a significant challenge to our current models of black hole growth and evolution. Conventional theories suggest that black holes form from the collapse of massive stars and then grow by accreting matter and merging with other black holes over billions of years. However, the existence of TON-618 in the early universe raises questions about how such an enormous black hole could have formed so quickly after the Big Bang. The immense size of TON-618 forces astronomers to consider alternative formation scenarios. One possibility is that this black hole formed from the direct collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. Another theory proposes that TON-618 might be the result of multiple mergers of smaller black holes in unusually dense galactic environments. These hypotheses challenge our understanding of early cosmic structures and the mechanisms of black hole growth. TON-618 serves as a cosmic laboratory, pushing scientists to refine their models and expand their understanding of the extreme physics at play in the formation of these cosmic giants. TON-618 is classified as a hypermassive quasar black hole. This extraordinary cosmic object stands out as one of the most massive black holes ever discovered in the observable universe. Located approximately 10 billion light-years from Earth, TON-618 is a prime example of a supermassive black hole that has grown to truly gargantuan proportions. What sets TON-618 apart is its staggering mass, estimated to be around 66 billion times that of our Sun. This colossal size places it firmly in the category of ultramassive black holes, a rare class of cosmic giants that push the boundaries of our understanding of black hole formation and growth. The immense gravitational pull of TON-618 allows it to consume vast amounts of surrounding matter, causing it to shine brightly as a quasar. Quasars are among the most luminous objects in the universe, powered by the intense energy released as material falls into the black hole. In the case of TON-618, Its quasar nature combined with its extraordinary mass makes it a unique and fascinating subject of study for astronomers and cosmologists. The existence of such an enormous black hole so early in the universe's history challenges our theories about how these cosmic behemoths form and evolve. Scientists continue to study TON-618 and similar objects to unravel the mysteries of black hole growth and their role in shaping the cosmos. Black holes are among the most enigmatic objects in the universe. They are regions of space where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. This extreme gravitational pull is caused by an enormous amount of mass compressed into an incredibly small volume. Black holes come in different sizes. Stellar black holes form when massive stars collapse at the end of their lives, while supermassive black holes, found at the centers of galaxies, can be millions or billions of times more massive than our Sun. Despite their name, black holes are not empty voids. They contain a singularity, a point where the laws of physics as we know them break down. The existence of black holes was first predicted by Einstein's theory of general relativity, but it took decades before astronomers found evidence of their existence. Today, we study black holes through their effects on nearby matter and the gravitational waves they produce when they collide. Black holes continue to challenge our understanding of the universe. They raise questions about the nature of space, time, and the fundamental laws of physics, making them a focal point of ongoing scientific research and exploration. Black holes form when massive stars reach the end of their lives and collapse under their own gravity. This process begins with stars at least 20 times more massive than our Sun. As these stellar giants exhaust their nuclear fuel, the delicate balance between gravity pulling inward and the outward pressure from fusion reactions is disrupted. Without the support of fusion, the star's core suddenly collapses. The outer layers of the star are violently ejected in a spectacular explosion called a supernova. Meanwhile, the remnant core continues to collapse, growing denser and denser. If the core is sufficiently massive, no known force can stop its collapse. As the core shrinks to a tiny volume, its gravitational pull becomes so intense that not even light can escape. This is the birth of a stellar black hole. The boundary beyond which nothing can escape is called the event horizon. Stellar black holes typically have masses between 5 and several dozen times that of our Sun. Supermassive black holes found at the centers of galaxies form through different processes. They likely grow over billions of years by merging with other black holes and consuming vast amounts of gas and dust. Some may have formed directly from the collapse of enormous gas clouds in the early universe. These cosmic titans can have masses millions or even billions of times greater than our Sun, shaping the evolution of entire galaxies. Black holes come in a variety of sizes and types, each with its own unique characteristics. Stellar black holes form when massive stars collapse at the end of their lives. These cosmic objects typically have masses ranging from about 5 to several tens of times that of our Sun. They are relatively small, often spanning just a few tens of kilometers across. At the other end of the scale are supermassive black holes. These giants lurk at the centers of most galaxies, including our own Milky Way. They can weigh millions or even billions of times the mass of our Sun. Despite their enormous mass, they are incredibly dense, with some being no larger than our solar system. Between these extremes lie intermediate mass black holes. These elusive objects are thought to range from about 100 to 100,000 solar masses. While their existence is still debated, recent observations have provided compelling evidence for their presence in some dense star clusters. There is also a hypothetical type called primordial black holes. These are thought to have formed in the early universe, not from collapsing stars, but from extremely dense regions present shortly after the Big Bang. If they exist, primordial black holes could range from microscopic sizes to massive scales, potentially explaining some of the universe's dark matter. The event horizon of a black hole marks a critical boundary in space. It is the point of no return, where the gravitational pull becomes so intense that nothing, not even light, can escape. This invisible barrier surrounds the black hole, separating the observable universe from the black hole's interior. At the event horizon, the laws of physics as we understand them begin to break down. Time and space become warped in extreme ways, leading to mind-bending effects. For an outside observer, an object falling towards the event horizon appears to slow down and freeze in time, never quite reaching the boundary itself. The size of an event horizon depends on the mass of the black hole. For a stellar black hole formed from a collapsed star, the event horizon might be just a few kilometers across. In contrast, supermassive black holes at the centers of galaxies can have event horizons millions of kilometers in diameter. Studying the event horizon presents immense challenges for scientists. Its nature makes direct observation impossible, forcing researchers to rely on indirect methods and advanced theoretical models to understand this cosmic phenomenon. Recent breakthroughs, such as the first image of a black hole's shadow, have provided tantalizing glimpses of these enigmatic cosmic objects and their event horizons. Black holes are cosmic powerhouses that warp the very fabric of space and time. As we approach a black hole, its immense gravitational pull begins to stretch and distort everything around it. This effect, known as gravitational time dilation, causes time to slow down near the black hole compared to regions farther away. An observer watching from a safe distance would see objects near the black hole moving in slow motion, while someone falling into the black hole would experience time passing normally. The space around a black hole becomes severely curved, creating what scientists call a gravity well. This curvature is so extreme that it can bend light, causing a phenomenon called gravitational lensing. Stars and galaxies behind the black hole may appear distorted or even duplicated when viewed from Earth, as their light follows the warped path of space around the cosmic behemoth. At the edge of a black hole lies the event horizon, a point of no return beyond which nothing can escape, not even light. This boundary marks where the gravitational pull becomes so strong that the escape velocity exceeds the speed of light. Inside the event horizon, our understanding of physics breaks down, and the laws of space and time as we know them cease to apply. The effects of a black hole extend far beyond its immediate vicinity. Supermassive black holes at the centers of galaxies play a crucial role in shaping the structure and evolution of their cosmic neighborhoods. Their gravitational influence can affect the orbits of stars and gas clouds, ultimately influencing the formation and distribution of matter throughout the galaxy. Gravitational lensing is a fascinating phenomenon that occurs when the immense gravity of massive objects bends the path of light. This effect is particularly pronounced around black holes, where gravity reaches its most extreme. As light from distant stars or galaxies passes near a black hole, it curves around the intense gravitational field, much like how a glass lens bends light. This bending can create multiple images of the same object, distort the appearance of distant galaxies, or even magnify the light from objects that would otherwise be too faint to see. Astronomers use gravitational lensing as a cosmic telescope, allowing them to study extremely distant and dim objects in the universe. Black holes, being the most gravitationally intense objects known, produce some of the most dramatic examples of gravitational lensing. The extreme curvature of space-time around a black hole can cause light to orbit it multiple times before escaping, creating a series of ghost images. In some cases, the lensing effect is so strong that it forms a complete ring of light around the black hole, known as an Einstein ring. Gravitational lensing by black holes not only helps astronomers study distant objects, but also provides a way to detect and study black holes themselves. By carefully analyzing the lensing effects, scientists can infer the mass and spin of black holes, gaining crucial insights into these enigmatic cosmic objects. Black holes are cosmic phenomena of unparalleled gravitational power, yet they are not entirely inescapable. While it is true that nothing can escape from within the event horizon, the boundary beyond which even light cannot break free, there is a fascinating exception known as Hawking radiation. Proposed by the renowned physicist Stephen Hawking, this theoretical form of radiation suggests that black holes are not entirely black. According to quantum mechanics, pairs of particles and antiparticles constantly pop into existence at the edge of a black hole. Occasionally, one particle falls into the black hole while the other escapes, effectively reducing the black hole's mass over time. Interestingly, supermassive black holes at the centers of galaxies also emit tremendous amounts of energy and matter in the form of jets. These powerful streams of particles and radiation can extend for thousands of light years, influencing the evolution of their host galaxies. However, it is important to note that this material originates from outside the event horizon, in the swirling accretion disk of matter surrounding the black hole. The concept of information escaping black holes has also been a topic of intense debate among physicists. The holographic principle suggests that information about everything that falls into a black hole might be preserved on its event horizon, potentially resolving the black hole information paradox. These ideas continue to challenge our understanding of the universe and push the boundaries of modern physics. Hawking radiation is a remarkable phenomenon theorized by the renowned physicist Stephen Hawking. This concept challenges our understanding of black holes, suggesting that these cosmic behemoths are not entirely black after all. According to Hawking's theory, black holes emit a faint glow of particles, slowly losing mass over time. This radiation arises from quantum effects near the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull. At this boundary, virtual particle pairs constantly pop into existence. Normally, these pairs would quickly annihilate each other. However, near a black hole, one particle might fall in while the other escapes, appearing as radiation to distant observers. This process leads to a gradual decrease in the black hole's mass and energy. For stellar mass black holes, this effect is incredibly slow, with the radiation being too faint to detect with current technology. However, for smaller black holes, the effect becomes more pronounced, potentially leading to their eventual evaporation. Hawking radiation connects the worlds of general relativity and quantum mechanics, two fundamental theories that have long resisted unification. It suggests that black holes are not eternal and unchanging, but dynamic objects that evolve over time, challenging our perceptions of these cosmic enigmas. Scientists employ several ingenious methods to detect black holes, despite their invisible nature. One primary technique involves observing the behavior of objects near suspected black holes. When stars or gas clouds orbit an unseen massive object, their movements reveal the presence of a strong gravitational pull. This method led to the discovery of Sagittarius A star, the supermassive black hole at the center of our Milky Way galaxy. Another detection method relies on gravitational lensing. Black holes can bend light from distant objects behind them, creating multiple images or distorting the appearance of these objects. By carefully analyzing these distortions, astronomers can infer the presence and properties of intervening black holes. X-ray emissions provide another crucial clue. As matter falls into a black hole, it forms an accretion disk that heats up to extreme temperatures, emitting powerful X-rays. Specialized space telescopes can detect these emissions, allowing scientists to locate and study black holes across the universe. Perhaps the most groundbreaking method in recent years is the detection of gravitational waves. When two black holes merge, they create ripples in space-time that can be measured by highly sensitive instruments on Earth. This technique has opened up a new era of black hole research, allowing scientists to observe events previously hidden from view and gain unprecedented insights into these cosmic giants. Black holes are crucial players in the cosmic drama of galaxy formation and evolution. These enigmatic objects, with their immense gravitational pull, act as cosmic architects, shaping the structure and dynamics of galaxies throughout the universe. At the heart of most large galaxies lies a supermassive black hole, millions or even billions of times more massive than our Sun. These cosmic giants exert a profound influence on their host galaxies. As matter falls into a supermassive black hole, it forms a swirling disk of gas and dust. This process releases enormous amounts of energy, creating what astronomers call an active galactic nucleus. The energy output from these active nuclei can regulate star formation within the galaxy, either suppressing it by heating up and expelling gas, or triggering it by compressing gas clouds. Black holes also play a role in galactic mergers, a common occurrence in the universe. When two galaxies collide, their central black holes eventually merge, releasing gravitational waves and reshaping the newly formed galaxy. This process can trigger bursts of star formation and alter the galaxy's structure. Furthermore, the relationship between a galaxy's central black hole and its overall properties, such as the velocity of stars in the galactic bulge, suggests a deep connection between black hole growth and galaxy evolution. This intricate dance between black holes and galaxies continues to shape our universe, influencing the cosmic landscape we observe today. Supermassive black holes are cosmic behemoths that lurk at the centers of most large galaxies, including our own Milky Way. Supermassive black holes are cosmic behemoths that lurk at the centers of most large galaxies, including our own Milky Way. These extraordinary objects are defined by their immense mass, which ranges from millions to billions of times that of our Sun. Their gravitational pull is so powerful that nothing, not even light, can escape once it crosses the event horizon, the point of no return. What sets supermassive black holes apart from their smaller counterparts is not just their size, but also their origin and evolution. While stellar black holes form from the collapse of massive stars, the formation of supermassive black holes is still a topic of intense research. Scientists believe they may have formed from the collapse of enormous gas clouds in the early universe, or grown over time by merging with other black holes and consuming vast amounts of matter. These cosmic giants play a crucial role in shaping the galaxies they inhabit. Their immense gravitational influence can regulate star formation and affect the distribution of matter throughout the galaxy. When actively feeding on surrounding material, supermassive black holes can become incredibly bright, outshining entire galaxies and becoming visible across vast cosmic distances as quasars or active galactic nuclei. Studying supermassive black holes provides valuable insights into the formation and evolution of galaxies, the nature of space-time, and the extreme physics that govern the universe. As our understanding of these enigmatic objects grows, so does our appreciation for their fundamental role in cosmic history and the structure of the universe as we know it. Supermassive black holes and stellar black holes are both cosmic phenomena that warp the fabric of space-time, but they differ vastly in scale and origin. Stellar black holes form when massive stars collapse at the end of their lives, typically resulting in objects a few times more massive than our Sun. These stellar remnants are relatively small, often spanning just a few dozen kilometers in diameter. In contrast, supermassive black holes are true cosmic giants, with masses ranging from millions to billions of times that of our Sun. They lurk at the centers of most large galaxies, including our own Milky Way. The size of these behemoths is staggering, with some having event horizons larger than our entire solar system. The formation of supermassive black holes remains a subject of intense study. Unlike their stellar counterparts, they are too massive to have formed from a single collapsing star. Scientists believe they may have grown over billions of years by consuming vast amounts of gas and dust, merging with other black holes, or perhaps forming from the direct collapse of enormous gas clouds in the early universe. Another key difference lies in their impact on their surroundings. While stellar black holes primarily affect nearby stars and gas, supermassive black holes can influence the structure and evolution of entire galaxies. Their immense gravitational pull can regulate star formation and shape the distribution of matter across cosmic scales, making them crucial players in the grand cosmic narrative. Supermassive black holes are typically found at the centers of large galaxies, including our own Milky Way. These cosmic giants are immensely powerful, with masses ranging from millions to billions of times that of our Sun. They exert a gravitational influence so strong that even light cannot escape their grasp. In most galaxies, these behemoths sit at the very heart of the cosmic structure, acting as a central anchor around which stars, gas, and dust orbit. Their presence significantly influences the evolution and behavior of their host galaxies. Some supermassive black holes are relatively quiet, while others are extremely active, consuming nearby matter and releasing enormous amounts of energy in the process. Astronomers have discovered that there appears to be a relationship between the mass of a supermassive black hole and the size of its host galaxy's central bulge. This suggests that these cosmic titans grow alongside their galactic homes, shaping each other's development over billions of years. Interestingly, recent observations have also revealed the existence of supermassive black holes in some unexpected locations, such as at the centers of dwarf galaxies or in seemingly empty regions of space. These findings continue to challenge our understanding of how these cosmic giants form and evolve. Supermassive black holes and galactic centers share an intimate and fascinating relationship. At the heart of nearly every large galaxy we observe, including our own Milky Way, lurks a supermassive black hole. These cosmic giants can have masses ranging from millions to billions of times that of our Sun. The presence of these enormous black holes significantly influences the structure and evolution of their host galaxies. As matter falls towards the black hole, it forms a swirling disk of gas and dust called an accretion disk. This process releases tremendous amounts of energy, often outshining the combined light of all the stars in the galaxy. This energetic output can have far-reaching effects on the surrounding galactic environment. It can heat up nearby gas, preventing it from cooling and forming new stars. In some cases, it can even expel gas from the galaxy entirely, effectively shutting down star formation on a galactic scale. Intriguingly, astronomers have discovered a correlation between the mass of a supermassive black hole and the mass of its host galaxy's central bulge. This relationship suggests a co-evolution between black holes and their galaxies, though the exact nature of this connection remains a subject of ongoing research and debate in the scientific community. Supermassive black holes, the titans of the cosmos, grow to their colossal sizes through a combination of voracious feeding and cosmic mergers. These behemoths, found at the hearts of most large galaxies, start their lives as smaller black holes, possibly formed from the collapse of massive stars. As they reside in the crowded centers of galaxies, these black holes have access to vast amounts of cosmic fuel. They devour surrounding gas, dust, and even entire stars, gradually increasing their mass. This process, known as accretion, can be incredibly efficient, allowing black holes to grow rapidly over millions or billions of years. But consumption is not the only path to growth. When galaxies collide, a common occurrence in the universe, their central black holes are drawn together by gravity. These black holes perform a cosmic dance, spiraling closer until they eventually merge. This union creates an even more massive black hole, combining the masses of its predecessors. This cycle of feeding and merging continues throughout cosmic history. The largest supermassive black holes we observe today, with masses equivalent to billions of suns, are the result of this long-term process of growth and collision. Their enormous size is a testament to the dynamic and often violent nature of our universe, where even the most powerful objects are subject to change and evolution. At the heart of galaxy Holm 15, A lies a colossal behemoth, a supermassive black hole of staggering proportions. This cosmic giant, with an estimated mass of 40 billion times that of our Sun, stands as a testament to the extreme phenomena that exist in our universe. While slightly smaller than TON-618, it still dwarfs most other known supermassive black holes by a considerable margin. The immense gravitational pull of this black hole has shaped the very structure of its host galaxy. Holm 15A, located approximately 700 million light-years from Earth, is classified as a brightest cluster galaxy, meaning it sits at the center of a large galaxy cluster. The presence of such a massive black hole at its core likely played a crucial role in the galaxy's formation and evolution. Astronomers discovered this cosmic giant through careful observations of the galaxy's central region. By studying the movements of stars near the galactic center, they were able to infer the presence and mass of the hidden black hole. This method, known as dynamical mass measurement, allows scientists to detect these invisible cosmic objects indirectly. The existence of such enormous black holes challenges our understanding of how these objects form and grow. It raises intriguing questions about the early universe and the processes that could lead to the creation of such massive cosmic entities. As we continue to explore the cosmos, discoveries like the black hole in Holm 15 push the boundaries of our knowledge and inspire further research into the nature of our universe. Supermassive black holes exert a profound influence on their host galaxies, shaping their evolution and structure in remarkable ways. These cosmic giants, residing at the hearts of most large galaxies, including our own Milky Way, have masses ranging from millions to billions of times that of our Sun. As these black holes consume nearby matter, they unleash tremendous amounts of energy in the form of radiation and powerful jets of particles. This process, known as active galactic nuclei feedback, can heat up and expel gas from the galaxy, effectively regulating star formation. In some cases, this feedback can halt star formation entirely, leading to what astronomers call galaxy quenching. The gravitational pull of supermassive black holes also affects the motion of stars and gas in the galactic center. This influence extends far beyond the immediate vicinity of the black hole, contributing to the overall structure and dynamics of the galaxy. Interestingly, astronomers have discovered a tight correlation between the mass of a supermassive black hole and the mass of its host galaxy's central bulge, suggesting a co-evolutionary relationship. Moreover, when galaxies merge, their central black holes can also combine, releasing enormous amounts of gravitational energy that can dramatically alter the merged galaxy's structure. This cosmic dance of galaxies and their central black holes plays a crucial role in shaping the universe we observe today. The M-sigma relation is a fascinating discovery in astrophysics that reveals a surprising connection between supermassive black holes and their host galaxies. This relation shows that the mass of a supermassive black hole at the center of a galaxy is closely linked to the velocity dispersion of stars in the galaxy's central bulge. Velocity dispersion refers to the spread of stellar velocities within a galaxy. In simpler terms, it measures how fast stars are moving in different directions. The Greek letter sigma is used to represent this velocity dispersion, hence the name M-sigma relation, where M stands for the mass of the black hole. What makes this relationship remarkable is its unexpected precision and universality. Regardless of a galaxy's size, age, or other properties, the mass of its central black hole consistently correlates with the velocity dispersion of stars in the galactic bulge. This tight correlation suggests a fundamental link between the growth of supermassive black holes and the evolution of their host galaxies. The M-sigma relation has profound implications for our understanding of galaxy formation and evolution. It indicates that the growth of supermassive black holes and the development of galaxies are intimately connected processes rather than separate phenomena. This discovery has led astronomers to rethink their models of galaxy evolution and consider how black holes might play a crucial role in shaping the universe we observe today. Supermassive black holes can indeed merge, and these cosmic collisions are among the most energetic events in the universe. When galaxies collide, which happens more often than one might think, their central supermassive black holes are drawn together by gravity. Over millions or even billions of years, these behemoths spiral ever closer, locked in a cosmic dance of unimaginable proportions. As they near each other, the black holes emit gravitational waves, ripples in the fabric of space-time that radiate outward at the speed of light. These waves carry away energy and angular momentum, causing the black holes to orbit each other even more closely. In the final moments before the merger, the black holes circle each other at nearly the speed of light, distorting space-time around them in extreme ways. The actual merger is an event of cosmic significance. When the black holes finally collide, they combine into a single, even more massive black hole. This process releases an enormous amount of energy in the form of gravitational waves, briefly outshining all the stars in the observable universe combined. However, this energy is not visible light, but rather ripples in space-time itself. Astronomers have detected several such mergers using gravitational wave detectors, though these have been smaller black holes, not the supermassive variety found at the centers of galaxies. The merger of supermassive black holes would produce even more powerful gravitational waves, potentially detectable by future space-based gravitational wave observatories. These observations could provide unprecedented insights into the nature of gravity, space-time, and the evolution of galaxies throughout cosmic history. When galaxies with supermassive black holes collide, a cosmic dance of immense proportions unfolds. These galactic mergers are among the most energetic events in the universe, releasing tremendous amounts of energy and reshaping vast regions of space. As the galaxies approach each other, their mutual gravitational pull causes them to distort and stretch. Streams of stars and gas are flung outward, forming long tidal tails that can extend for hundreds of thousands of light years. The supermassive black holes at the centers of these galaxies begin a slow journey towards each other, drawn inexorably closer by gravity. During this process, the black holes don't immediately merge. Instead, They orbit each other in a cosmic waltz that can last millions of years. As they circle, they consume surrounding matter at an accelerated rate, causing them to grow even more massive. This increased activity often triggers bursts of energy across the electromagnetic spectrum, making colliding galaxies some of the brightest objects in the universe. Eventually, the black holes come close enough for their event horizons to touch, and they merge into a single, even more massive black hole. This final merger releases enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time that spread across the universe at the speed of light. The resulting galaxy, now hosting a single supermassive black hole, settles into a new configuration, forever changed by this cosmic collision. The precise age of TON-618, the ultramassive black hole at the center of a distant quasar, is challenging to determine with certainty. However, based on our understanding of quasar formation and the early universe, astronomers estimate that TON-618 likely formed when the universe was relatively young, perhaps around 1 billion to 1.5 billion years after the Big Bang. This estimate places the birth of TON-618 in the early stages of galaxy formation, during a period known as the Cosmic Dawn. At this time, the first stars and galaxies were emerging from the primordial gas that filled the young universe. The rapid growth of supermassive black holes like TON-618 during this era remains a subject of intense study and debate among astrophysicists. The age of TON-618 is intrinsically linked to its enormous size. Its incredible mass, estimated at 66 billion times that of our Sun, suggests a long period of growth and accretion. This growth would have occurred through the consumption of vast amounts of matter and possibly through mergers with other black holes. Understanding the age and formation of objects like TON-618 is crucial for unraveling the mysteries of galaxy evolution and the role of supermassive black holes in shaping the cosmos we observe today. As our observations and models improve, we may refine our estimates of TON-618's age and gain deeper insights into the processes that led to its formation. The universe is approximately 13.8 billion years old. This age estimate comes from a variety of scientific observations and measurements, including studies of the cosmic microwave background radiation and the expansion rate of the universe. Astronomers and cosmologists have refined this estimate over decades using increasingly sophisticated instruments and techniques. The age of the universe is closely tied to the Big Bang theory, which posits that the universe began as an incredibly hot, dense state and has been expanding ever since. By measuring how fast the universe is expanding today and extrapolating backward, scientists can calculate when this expansion began, giving us the age of the universe. This 13.8 billion-year timescale is difficult for human minds to fully comprehend. To put it in perspective, if the entire history of the universe were compressed into a single year, modern humans would only appear in the last few seconds before midnight on December 31st. Our solar system, including Earth, formed roughly 4.6 billion years ago, meaning the universe was already over 9 billion years old when our planet came into existence. Understanding the age of the universe is crucial for many areas of scientific research, from the study of galaxy formation to the evolution of cosmic structures. It provides a framework for understanding the timescales of cosmic processes and helps us place our own existence in the grand cosmic context. TON-618 cannot be older than the universe. This supermassive black hole, one of the largest known, presents a fascinating puzzle for astronomers and cosmologists. The challenge lies not in its age, but in its immense size given the age of the universe. Current estimates place the age of the universe at about 13.8 billion years. TON-618, like all observed celestial objects, must be younger than this. The quasar powered by this black hole is observed as it appeared when the universe was only about 1 billion years old. This means the black hole had to grow to its enormous size incredibly quickly, in cosmic terms. The rapid growth of TON-618 to such a massive size in a relatively short period poses questions about our understanding of black hole formation and growth. Scientists are working to explain how such a large black hole could form so early in the universe's history. Theories include the possibility of unusually large seed black holes, extremely rapid accretion of matter, or even the merging of multiple smaller black holes. This apparent paradox of TON-618's size rather than its age challenges our current models of the early universe and continues to drive research in cosmology and astrophysics. It serves as a reminder that the universe still holds many mysteries waiting to be unraveled. Several theories have been proposed to address the age paradox in our universe. One prominent explanation is cosmic inflation, which suggests that the universe underwent a period of rapid expansion in its earliest moments. This theory posits that the universe grew exponentially for a fraction of a second after the Big Bang, expanding faster than the speed of light. Cosmic inflation would explain how regions of the universe that appear too far apart to have ever been in contact can share similar properties. Another approach involves the concept of a cyclic universe, where our current universe is just one in a series of expansions and contractions. This model proposes that the universe goes through cycles of big bangs and big crunches, potentially resolving the issue of how the universe could appear older than its calculated age. Some scientists have also explored the idea of variable speed of light theories. These suggest that the speed of light might have been much faster in the early universe, allowing for more rapid information exchange and equilibration across vast distances. While controversial, this concept offers an alternative explanation for the uniformity we observe. Quantum entanglement on a cosmic scale has also been proposed as a potential solution. This theory suggests that quantum effects in the early universe could have created correlations across vast distances, explaining the observed homogeneity without violating the speed of light limit. These theories continue to be debated and refined as new observations and data become available. The supermassive black hole TON-618 presents a significant challenge to our understanding of cosmic evolution due to its extraordinary age and size. This colossal object, residing at the center of a distant quasar, is estimated to have formed when the universe was less than 1 billion years old. Yet, it already possessed a mass equivalent to 66 billion suns, making it one of the most massive black holes ever discovered. The existence of such an enormous black hole so early in cosmic history forces astronomers to reconsider the timelines and mechanisms of black hole formation and growth. Traditional models suggest that black holes start small and gradually accumulate mass over billions of years. However, TON-618 appears to have grown to its immense size in a fraction of that time, defying conventional growth rates. This rapid growth raises questions about the availability of matter in the early universe and the efficiency of accretion processes. Scientists are now exploring alternative theories, such as the direct collapse of massive gas clouds or the merger of multiple primordial black holes, to explain the presence of these cosmic giants in the young universe. The age of TON-618 also impacts our understanding of galaxy formation and evolution. The relationship between supermassive black holes and their host galaxies is complex, with each influencing the other's growth. The presence of such a massive black hole in the early universe suggests that some galaxies may have evolved more rapidly than previously thought, altering our timeline of cosmic structure formation. The extreme age of TON-618, estimated to be around 13 billion years old, challenges our understanding of early universe formation and the growth of supermassive black holes. This quasar, containing one of the most massive known black holes, existed when the universe was less than 1 billion years old. Its presence so early in cosmic history forces us to reconsider how quickly such enormous structures can form. Traditional models suggest that supermassive black holes grow gradually by accreting matter and merging with other black holes over billions of years. However, the existence of TON-618 in the early universe indicates that some black holes must have grown at rates far exceeding our previous estimates. This rapid growth could imply that the seeds of these black holes were already quite massive, possibly formed from the direct collapse of enormous gas clouds in the early universe. The age of TON-618 also provides valuable insights into the conditions of the early universe. Its existence suggests that the cosmic environment at that time was conducive to the formation and rapid growth of supermassive black holes. This could mean that the early universe was denser and richer in gas than previously thought, providing ample fuel for these cosmic titans to grow quickly. Furthermore, The age of TON-618 has implications for our understanding of galaxy formation and evolution. The relationship between supermassive black holes and their host galaxies is complex, with each influencing the other's growth. The presence of such a massive black hole so early in cosmic history suggests that some galaxies may have evolved more rapidly than our models predict, pushing us to refine our theories of galactic evolution in the early universe. Cosmic inflation and the age of TON-618 are intricately connected through the lens of our understanding of the early universe. Cosmic inflation refers to the theory that the universe underwent a period of rapid expansion in its first fraction of a second, growing exponentially in size. This process set the stage for the formation of the first stars and galaxies. TON-618, one of the most massive known quasars, presents a fascinating puzzle when we consider its age in relation to cosmic inflation. This supermassive black hole, powering an incredibly bright quasar, is estimated to have formed when the universe was less than 1 billion years old. Its existence so early in cosmic history challenges our models of black hole formation and growth. The rapid expansion during the inflationary period could have created the conditions necessary for the formation of massive seed black holes. These seeds might have then grown rapidly, fed by the abundant matter in the early universe, to become behemoths like TON-618 in a relatively short cosmic time frame. However, the presence of such a massive object so soon after the Big Bang and cosmic inflation pushes the limits of our current understanding. It suggests that either our models of black hole growth need revision, or that the processes in the very early universe, including cosmic inflation, might have played a more significant role in seeding large cosmic structures than previously thought. The supermassive black hole TON-618, located in a quasar billions of light-years from Earth, is one of the most massive known black holes in the observable universe. Its incredible size, estimated at 66 billion times the mass of our Sun, raises intriguing questions about its origin and formation. While the concept of a previous universe cycle is fascinating, current scientific understanding does not support the idea that TON-618 could have formed in a prior cosmic iteration. The prevailing cosmological model, known as lambda cold dark matter, describes our universe as having a definite beginning with the Big Bang about 13.8 billion years ago. Instead, astronomers believe that TON-618 likely formed through a combination of processes in the early universe. These may include the rapid collapse of massive gas clouds, mergers of smaller black holes, and the accretion of vast amounts of matter over billions of years. The presence of such an enormous black hole so early in cosmic history challenges our understanding of black hole growth and galaxy formation. Ongoing research into primordial black holes, quantum fluctuations in the early universe, and the nature of dark matter may provide new insights into how these cosmic giants came to be. While we cannot definitively rule out more exotic explanations, the formation of TON-618 within our current universe remains the most plausible scenario based on our current knowledge. Dark energy, the mysterious force causing the accelerated expansion of our universe, could potentially play a significant role in explaining the age of TON-618, one of the most massive black holes ever discovered. This supermassive black hole, located billions of light-years away from Earth, presents a puzzle for astronomers due to its enormous size and the early epoch in which it formed. The presence of dark energy might have influenced the growth rate of TON-618 in several ways. As dark energy pushes galaxies apart, it could have affected the availability of matter for the black hole to consume. This cosmic expansion might have initially provided TON-618 with a rich supply of nearby material, allowing it to grow rapidly in its early stages. Furthermore, dark energy's effect on the fabric of space-time could have implications for our understanding of time in the early universe. The accelerated expansion caused by dark energy might have altered the rate at which time passed in the vicinity of TON-618, potentially allowing more time for growth than our current models suggest. However, it is important to note that the relationship between dark energy and black hole formation is still a topic of ongoing research. Scientists continue to develop and refine theories to explain how such massive black holes could have formed so early in the history of the universe and the role of dark energy in this process remains an intriguing area of study. Quantum mechanics plays a crucial role in our understanding of supermassive black holes like TON-618, influencing theories about their formation and growth. At the heart of these cosmic giants, quantum effects become increasingly important, challenging our classical notions of space and time. The origin of TON-618, one of the most massive known black holes in the universe, likely involves quantum processes operating in the early universe. These primordial black holes could have served as the seeds for the behemoth we observe today. Furthermore, quantum mechanics governs the behavior of matter at the event horizon of TON-618. The quantum nature of particles leads to phenomena like Hawking radiation, where virtual particle pairs are created near the black hole's edge. This process, while incredibly slow for such a massive black hole, affects its long-term evolution and interactions with surrounding matter. Quantum entanglement, another key concept in quantum mechanics, might also play a role in the information paradox associated with black holes like TON-618. This paradox challenges our understanding of how information is preserved or lost when matter falls into a black hole, pushing the boundaries of our current theories and driving the search for a unified theory of quantum gravity. TON-618, a distant and extremely luminous quasar, has been the subject of observation by several powerful telescopes. The Sloan Digital Sky Survey, a major multi-filter imaging and spectroscopic survey, was instrumental in gathering detailed data about this extraordinary cosmic object. This survey used a dedicated 2.5-meter wide-angle optical telescope at Apache Point Observatory in New Mexico. The Hubble Space Telescope has also been utilized to study TON-618, providing high-resolution images and spectroscopic data. Hubble's advanced instruments, operating above Earth's atmosphere, allow for exceptionally clear observations of distant celestial bodies like TON-618. Ground-based telescopes such as the Very Large Telescope in Chile have contributed to our understanding of TON-618. The Very Large Telescope consists of 4 main telescopes, each with a mirror 8.2 meters in diameter, working together to provide detailed observations of distant cosmic phenomena. Radio telescopes have also played a role in studying TON-618, as quasars emit significant amounts of radio waves. The Very Large Array in New Mexico, comprising 27 radio antennas, has been used to collect valuable data about this enigmatic quasar and its surrounding environment. Astronomers employ a wide range of wavelengths to study TON-618, one of the most massive known black holes in the universe. Radio waves play a crucial role in observing this distant quasar, allowing scientists to detect emissions from the powerful jets of material expelled by the black hole. These radio observations help map the structure and behavior of TON-618's surrounding environment. Optical light is also vital for studying TON-618, as it enables researchers to analyze the quasar's visible emissions and gather data about its luminosity and composition. Infrared wavelengths prove particularly useful for penetrating cosmic dust and observing the heat signatures associated with the intense activity around the supermassive black hole. X-rays and gamma rays are equally important in the study of TON-618. These high-energy wavelengths provide insights into the extreme processes occurring near the black hole's event horizon, where matter is heated to incredible temperatures as it spirals inward. By combining observations from multiple wavelengths, scientists can build a comprehensive picture of TON-618's properties and behavior. Ultraviolet light observations complement the other wavelengths, revealing information about the hot gas in the quasar's accretion disk and the surrounding regions. This multi-wavelength approach allows astronomers to unravel the complexities of TON-618 and further our understanding of supermassive black holes and their role in galactic evolution. TON-618 was first detected in 1970 during a survey of celestial objects emitting strong radio waves. This survey, known as the Third Ohio State University Radio Survey, scanned the sky for peculiar radio sources. The name TON-618 comes from this survey, with TON standing for Third Ohio State University Radio Catalog. Initially, astronomers thought TON-618 was just another quasar, an extremely bright and distant object powered by a supermassive black hole. However, further observations revealed that it was no ordinary quasar. Its exceptional brightness and unique characteristics set it apart from other known objects in the universe. Subsequent studies using various telescopes and instruments across different wavelengths of light provided more detailed information about TON-618. These observations helped astronomers understand its true nature and estimate its incredible mass and size. The discovery and ongoing study of TON-618 highlight the importance of sky surveys in identifying extraordinary cosmic objects. It also demonstrates how our understanding of the universe continues to evolve as we develop more advanced observational techniques and technologies. Quasars are among the brightest and most energetic objects in the universe. These cosmic powerhouses are found at the centers of distant galaxies and are driven by supermassive black holes actively consuming surrounding matter. As material falls into the black hole, it forms a swirling disk of gas and dust that becomes superheated, emitting intense radiation across the electromagnetic spectrum. TON-618 is an extraordinary example of a quasar, discovered in the 1970s and located approximately 10 billion light-years from Earth. What sets TON-618 apart is the sheer scale of its central black hole. Scientists estimate that this behemoth contains a mass equivalent to 66 billion suns, making it one of the most massive black holes ever detected. The enormous size of TON-618's black hole allows it to consume vast amounts of matter, resulting in an exceptionally luminous quasar. Its brightness is so intense that it outshines entire galaxies, making it visible across cosmic distances despite its great distance from Earth. This extreme luminosity is what enables astronomers to study such distant objects and gain insights into the early universe. TON-618 serves as a prime example of how quasars can help us understand the formation and evolution of galaxies and supermassive black holes. By studying this and other quasars, scientists can piece together the cosmic story of how these gargantuan objects came to exist and how they have influenced the development of the universe over billions of years. TON-618, the most massive known black hole in the observable universe, shows clear signs of active feeding. This colossal black hole, residing at the center of a distant quasar, exhibits intense energy output that can only be explained by ongoing accretion of matter. Astronomers have detected powerful jets of particles streaming from the vicinity of TON-618 at nearly the speed of light. These jets are a telltale sign of an actively feeding black hole, as they are formed by material that gets heated and accelerated as it falls towards the event horizon. The immense energy required to produce such jets can only come from the gravitational energy released as matter plunges into the black hole. Furthermore, the quasar hosting TON-618 emits an extraordinary amount of light, making it one of the brightest objects in the universe. This intense luminosity is generated by the accretion disk surrounding the black hole, wherein falling matter is heated to extreme temperatures due to friction and compression. The sheer brightness of this quasar indicates that TON-618 is consuming matter at a prodigious rate. Spectroscopic observations of TON-618 reveal broad emission lines, characteristic of gas moving at very high velocities near the black hole. These emission lines provide evidence of the turbulent environment around TON-618, where vast amounts of material are being drawn in and devoured by the insatiable gravitational pull of this cosmic giant. Measuring the mass of a supermassive black hole like TON-618 requires ingenious techniques and advanced technology. Astronomers cannot directly weigh these cosmic giants, so they rely on indirect methods to estimate their immense mass. One key approach involves observing the motion of gas and stars around the black hole. The gravitational pull of TON-618 affects everything in its vicinity, causing nearby objects to orbit at incredible speeds. By carefully measuring these orbital velocities, scientists can calculate the black hole's mass using the principles of gravity and motion established by Isaac Newton. Another method utilizes the relationship between a black hole's mass and the brightness of its surrounding accretion disk. As matter falls towards TON-618, it forms a swirling disk of superheated gas that emits intense radiation. The amount of light produced by this accretion disk is directly related to the black hole's mass, allowing astronomers to make accurate estimates. Additionally, scientists use spectroscopy to analyze the light emitted by gas near the black hole. The extreme gravitational forces around TON-618 cause the light to be redshifted or stretched to longer wavelengths. By measuring this redshift, researchers can determine the black hole's gravitational influence and, consequently, its mass. These combined techniques have revealed that TON-618 is one of the most massive known black holes in the universe, with a mass of approximately 66 billion times that of our Sun. TON-618 is a hyperluminous quasar, one of the most powerful and brightest objects in the known universe. At its heart lies an ultramassive black hole, surrounded by a vast accretion disk of superheated gas and dust. This disk is a swirling maelstrom of matter stretching across a distance greater than our entire solar system. The accretion disk of TON-618 is a cosmic powerhouse, radiating energy across the electromagnetic spectrum. As matter in the disk spirals inward towards the black hole, it heats up to millions of degrees, emitting intense radiation that we can detect from Earth. This radiation provides astronomers with crucial information about the black hole and its environment. By studying the spectrum of light from the accretion disk, scientists can determine the temperature, composition, and velocity of the material within it. This information helps us understand the physics of extreme environments and the processes that drive the most energetic phenomena in the universe. The sheer brightness of TON-618's accretion disk also gives us clues about the size and mass of the central black hole. Current estimates suggest this black hole could be more than 66 billion times the mass of our Sun, making it one of the largest known black holes in the universe. The accretion disk thus serves as a cosmic laboratory, allowing us to test our theories of gravity and the behavior of matter under the most extreme conditions imaginable. The powerful jets emanating from TON-618 offer astronomers a wealth of information about this extraordinary supermassive black hole. These jets, composed of high-energy particles and radiation, stretch for thousands of light-years into intergalactic space. By studying their composition, speed, and structure, scientists can deduce crucial details about the black hole's size, spin, and the intense environment surrounding it. The jet's immense power indicates that TON-618 is actively feeding on surrounding matter, forming an accretion disk that heats up to extreme temperatures. This process releases enormous amounts of energy, some of which is channeled into the jets. The jet's velocity, approaching the speed of light, reveals the incredible gravitational forces at play near the black hole's event horizon. Observations of these jets across different wavelengths of light provide insights into the magnetic fields around TON-618. These fields play a crucial role in shaping and accelerating the jets. The jet's stability and extent also hint at the black hole's longevity and its impact on the surrounding galactic environment. Furthermore, the jets serve as cosmic beacons, allowing astronomers to locate and study this distant black hole. Their brightness and distinctive features make TON-618 observable from Earth despite its vast distance, enabling ongoing research into one of the most massive known black holes in the universe. The Hubble Space Telescope has been instrumental in studying TON-618, providing crucial observations that have advanced our understanding of this extraordinary object. As one of the most powerful space observatories ever built, Hubble has allowed astronomers to peer deep into the cosmos and examine distant celestial bodies with unprecedented clarity. TON-618 is a quasar, an incredibly bright and energetic object powered by a supermassive black hole at the center of a galaxy. What makes this particular quasar remarkable is its sheer size and power. Hubble's observations have helped confirm that TON-618 hosts one of the most massive black holes ever discovered, with an estimated mass of 66 billion times that of our Sun. The telescope's ability to capture high-resolution images and spectra across various wavelengths has enabled scientists to study the quasar's structure and composition in detail. These observations have revealed the intense radiation emitted by the accretion disk surrounding the black hole, as well as the powerful jets of material being ejected from its poles. Furthermore, Hubble's data has allowed researchers to estimate the distance to TON-618, placing it at approximately 10.4 billion light-years away from Earth. This information is crucial for understanding the quasar's place in the cosmic timeline and its role in the early universe. By studying objects like TON-618, scientists can gain insights into the formation and evolution of galaxies and supermassive black holes over cosmic time. Future telescopes will revolutionize our study of TON-618, the gargantuan black hole that dwarfs most others in the known universe. As technology advances, we'll gain unprecedented views of this cosmic behemoth and its surrounding environment. Next-generation space telescopes, with their enhanced sensitivity and resolution, will allow us to peer deeper into the heart of TON-618. We'll be able to observe the swirling disk of matter around the black hole with greater clarity, revealing intricate details about how it consumes nearby stars and gas. These observations will provide crucial data on the mechanics of supermassive black hole feeding and growth. Ground-based telescopes equipped with advanced adaptive optics will complement space-based observations. By correcting for atmospheric distortions, these instruments will capture sharper images of TON-618's host galaxy. This will help scientists better understand the relationship between the black hole and its galactic environment, shedding light on how such an enormous black hole could have formed. Perhaps most excitingly, future gravitational wave detectors might be sensitive enough to detect ripples in spacetime caused by events near TON-618. This could offer an entirely new way to study the black hole, potentially revealing hidden aspects of its behavior and challenging our current theories about the nature of these cosmic giants. TON-618 resides in a galaxy that stands out as truly extraordinary. This distant cosmic structure is classified as a quasar, one of the most luminous and energetic objects in the universe. The host galaxy itself is difficult to observe directly due to the overwhelming brightness of the quasar at its core. The central region of this galaxy harbors a supermassive black hole of staggering proportions. This cosmic titan is estimated to have a mass of 66 billion times that of our Sun, making it one of the most massive black holes ever discovered. Its immense gravitational pull shapes the entire galaxy around it, influencing the movement and formation of stars across vast distances. The quasar at the heart of this galaxy outshines the combined light of all the stars within it. This intense luminosity is produced by the incredible amounts of matter being consumed by the central black hole, creating a swirling disk of superheated gas that emits enormous amounts of energy across the electromagnetic spectrum. Despite its extreme nature, the galaxy hosting TON-618 likely shares some similarities with other large galaxies. It probably contains billions of stars, vast clouds of gas and dust, and potentially even smaller satellite galaxies orbiting around it. However, the dominant feature remains the blindingly bright quasar at its center, a cosmic beacon visible across billions of light-years of space. TON-618, the largest known black hole in the observable universe, exerts an immense gravitational influence on its surroundings. This supermassive behemoth, with a mass equivalent to 66 billion suns, dramatically alters the fabric of space and time in its vicinity. The intense gravitational pull of TON-618 affects nearby stars in several ways. It accelerates them to extraordinary speeds as they orbit the black hole, causing them to complete revolutions in mere decades rather than the millions of years typical for galactic orbits. This rapid motion heats the stars, causing them to burn brighter and potentially altering their life cycles. Gas clouds near TON-618 experience even more extreme effects. As gas spirals towards the black hole, it forms a swirling accretion disk. Friction within this disk heats the gas to millions of degrees, causing it to glow intensely across multiple wavelengths of light. This process releases enormous amounts of energy, making TON-618 one of the brightest objects in the universe. The black hole's gravity also creates powerful jets of plasma that shoot out from its poles at nearly the speed of light. These jets can extend for thousands of light years, influencing gas and dust far beyond the immediate vicinity of the black hole. The combination of gravitational forces, intense radiation, and plasma jets makes the region around TON-618 an extreme and dynamic environment, constantly shaping and reshaping the surrounding cosmic landscape. The material surrounding TON-618, one of the most massive black holes known to astronomers, experiences extreme temperatures. As matter spirals towards this supermassive black hole, it forms an accretion disk that heats up due to intense friction and gravitational forces. The innermost regions of this disk can reach temperatures of millions of degrees Celsius. This scorching environment is so hot that atoms break apart, creating a soup of subatomic particles. The extreme heat causes the accretion disk to emit vast amounts of energy across the electromagnetic spectrum, including X-rays and ultraviolet light. This intense radiation is what makes TON-618 visible to us from billions of light-years away. As we move further from the black hole, the temperature gradually decreases. However, even at greater distances, the environment remains incredibly hostile by earthly standards. The entire region around TON-618 is a cosmic furnace, showcasing the immense energy and heat generated by the most extreme objects in our universe. At the heart of the quasar, TON-618 lies a supermassive black hole of staggering proportions. The matter swirling around this cosmic behemoth moves at mind-boggling speeds. As material approaches the event horizon, it accelerates to velocities nearing half the speed of light. This means that the innermost parts of the accretion disk are hurtling through space at roughly 150,000 kilometers per second. To put this into perspective, at such speeds, you could theoretically circle the Earth more than 3 times in a single second. The extreme velocities are a result of the black hole's immense gravitational pull, which becomes stronger as matter gets closer to the event horizon. These incredible speeds also contribute to the intense energy output of TON-618. As matter in the accretion disk collides and heats up due to friction, it releases enormous amounts of energy in the form of radiation, making TON-618 one of the brightest objects in the known universe. The rapid orbital velocities around TON-618 serve as a testament to the unimaginable power of supermassive black holes and the extreme environments they create in the cosmos. TON-618, the supermassive black hole that holds the record for being the most massive known black hole in the observable universe, resides in a quasar located in the constellation Canes Venatici. While this extraordinary object dominates its local space, there are indeed other celestial bodies of interest in its vicinity. The region surrounding TON-618 contains numerous galaxies, as it is part of a larger cosmic structure. Several galaxy clusters and superclusters populate this area of space, forming an intricate web of cosmic matter. These structures, though pale in comparison to the immense gravitational influence of TON-618, play crucial roles in shaping the cosmic landscape. Interestingly, astronomers have detected other quasars in the general vicinity of TON-618. These quasars, while not as massive or luminous as TON-618, are still incredibly energetic phenomena powered by their own supermassive black holes. Their presence suggests that this region of the universe was particularly active in terms of galaxy formation and black hole growth during earlier cosmic epochs. It is worth noting that our understanding of the immediate neighborhood of TON-618 is limited by its extreme distance from Earth and the challenges associated with observing objects at such vast cosmic scales. As our observational technologies continue to advance, we may uncover more details about the celestial environment surrounding this cosmic giant, potentially revealing even more fascinating objects and structures in its cosmic vicinity. TON-618, a supermassive black hole of extraordinary proportions, exerts a profound influence on star formation in its cosmic neighborhood. This colossal object, with a mass estimated to be 66 billion times that of our Sun, creates an environment of extreme gravitational forces and intense radiation that significantly impacts the surrounding space. The immense gravity of TON-618 draws in vast amounts of gas and dust from its vicinity, forming a swirling accretion disk around the black hole. As this material heats up and becomes compressed, it emits powerful radiation and energetic jets. These intense outflows can trigger star formation in some regions by compressing gas clouds, while simultaneously suppressing it in others by dispersing or heating the gas beyond the point where it can collapse to form stars. The radiation from TON-618 ionizes large volumes of gas in its host galaxy and beyond, creating vast bubbles of hot plasma. This process, known as feedback, can have both positive and negative effects on star formation. In some cases, it may compress gas clouds and initiate star birth, while in others, it may heat the gas to temperatures too high for stars to form. The extreme environment around TON-618 likely results in the formation of massive, short-lived stars rather than smaller, longer-lived ones. This preference for large stars could lead to rapid cycles of star formation and destruction, profoundly shaping the evolution of its host galaxy and potentially influencing neighboring galaxies as well. The gravitational influence of TON-618, one of the most massive black holes known to exist, extends far beyond what we typically encounter in our cosmic neighborhood. This ultra-massive black hole, residing at the center of a distant quasar, exerts an immense gravitational pull that shapes the space around it for an extraordinary distance. To put its influence into perspective, TON-618's gravitational reach extends well beyond the boundaries of what we would consider a typical galaxy. Its gravitational effects are felt across a region spanning millions of light-years, influencing the movement and distribution of gas, dust, and even entire star systems within this vast expanse. The sheer power of TON-618's gravity is so intense that it warps the fabric of space-time itself, creating a deep gravitational well that affects the trajectory of light passing nearby. This phenomenon, known as gravitational lensing, can bend and magnify light from distant objects behind the black hole, providing astronomers with a cosmic magnifying glass to study the far reaches of the universe. Moreover, the gravitational influence of TON-618 plays a crucial role in shaping the evolution and structure of its host galaxy. It regulates star formation, influences the distribution of matter, and even affects the motion of satellite galaxies that may orbit within its gravitational domain. This expansive reach demonstrates the profound impact that supermassive black holes can have on their cosmic surroundings, making TON-618 a prime example of the interconnectedness of cosmic structures across vast distances. TON-618 stands out as an exceptional supermassive black hole, dwarfing most others in the known universe. Its environment is characterized by extreme conditions that push the boundaries of our understanding of cosmic phenomena. The black hole itself is estimated to have a mass of 66 billion times that of our Sun, making it one of the most massive black holes ever discovered. The region surrounding TON-618 is a maelstrom of intense activity. It sits at the heart of a quasar, one of the brightest objects in the universe. This quasar outshines entire galaxies, powered by the immense gravitational forces of the black hole pulling in vast amounts of matter. As this material falls towards TON-618, it forms a swirling accretion disk that heats up to incredible temperatures, releasing enormous amounts of energy across the electromagnetic spectrum. Compared to other supermassive black holes, the environment around TON-618 is exceptionally energetic and turbulent. The gravitational influence of this behemoth extends much further into space than that of smaller supermassive black holes, affecting a larger region of its host galaxy. The intense radiation from the quasar likely impacts star formation and galactic evolution on a grand scale, potentially stunting or triggering the birth of new stars in its vicinity. The sheer size and power of TON-618 create an environment that is more extreme in every aspect than what we observe around most other supermassive black holes. Its study continues to challenge our theories and expand our understanding of the most massive objects in the cosmos. The environment surrounding TON-618 offers crucial insights into its tumultuous past. This hyperluminous quasar, one of the most energetic objects in the known universe, resides at the heart of a massive galaxy. The immense gravitational influence of TON-618 has left an indelible mark on its cosmic neighborhood. Observations of the surrounding region reveal a relative scarcity of nearby galaxies, suggesting that TON-618 may have consumed or scattered its galactic neighbors over billions of years. This process of galactic cannibalism has likely contributed to the quasar's extraordinary size and luminosity. The few galaxies that do exist in proximity to TON-618 show signs of disruption and distortion, their structures warped by the quasar's gravitational pull. The intergalactic medium around TON-618 also tells a story of intense activity. Astronomers have detected vast bubbles of hot gas extending far beyond the quasar's host galaxy. These bubbles, inflated by powerful outflows from the quasar, act as cosmic fossils, preserving evidence of past eruptions and periods of intense activity. Furthermore, the chemical composition of the surrounding space provides clues about TON-618's history. The presence of heavy elements in the intergalactic medium suggests that the quasar has been expelling material from its host galaxy for eons, enriching the space around it with the products of stellar evolution and supermassive black hole activity. The environment surrounding TON-618, the most massive known black hole in the observable universe, will undergo dramatic changes over cosmic timescales. As this supermassive black hole continues to consume nearby matter, its gravitational influence will expand, altering the galactic landscape around it. Over millions of years, TON-618 will likely merge with other black holes in its vicinity, growing even more massive. This process will send gravitational waves rippling through space, potentially disrupting the orbits of nearby stars and gas clouds. The intense radiation emitted from the accretion disk around TON-618 will ionize surrounding gas, creating vast bubbles of hot plasma that extend far into intergalactic space. As eons pass, the galaxy hosting TON-618 may cannibalize smaller neighboring galaxies, drawn in by the black hole's immense gravity. This galactic merger process will trigger bursts of star formation, temporarily illuminating the region with the light of newly born stars. However, the voracious appetite of TON-618 will eventually deplete the available gas and dust, leading to a decline in star formation. In the far future, as the universe continues to expand and cool, the area around TON-618 may become an island of activity in an increasingly dark cosmos. The black hole's immense mass could allow it to continue accreting material long after smaller black holes have gone dormant, making it one of the last beacons of energy in a fading universe. TON-618, the ultramassive black hole at the center of a distant quasar, grew to its enormous size through a combination of processes over billions of years. This cosmic behemoth, with a mass equivalent to 66 billion suns, likely began as a smaller seed black hole in the early universe. As the universe evolved, this seed black hole voraciously consumed surrounding matter, including gas, dust, and even entire stars. The intense gravitational pull of the growing black hole drew in material from its host galaxy, forming a swirling accretion disk around it. This disk became superheated due to friction and intense pressure, causing it to glow brightly and emit vast amounts of energy, creating the quasar we observe today. TON-618 might have also grown through mergers with other black holes as galaxies collided and combined over cosmic time. These mergers would have rapidly increased its mass, allowing it to exert even greater gravitational influence on its surroundings and accelerate its growth further. The extraordinary size of TON-618 suggests that it may have formed in an unusually dense region of the early universe, where abundant material was available for consumption. Its growth might have been particularly rapid during the first few billion years after the Big Bang, when the universe was more compact and material was more readily available for black holes to devour. At the heart of the quasar, TON-618 lies an ultramassive black hole, one of the largest ever discovered. This cosmic behemoth fuels its incredible growth through a process of voracious accretion. As the black hole's immense gravity pulls in surrounding matter, it forms a swirling disk of gas and dust around the event horizon. This material, heated to extreme temperatures by friction and compression, radiates enormous amounts of energy across the electromagnetic spectrum. The accretion disk acts as a cosmic buffet for the black hole, providing a constant supply of matter to consume. As material from the disk falls towards the event horizon, it is accelerated to near light speed, releasing tremendous amounts of energy in the process. This energy output is so intense that TON-618 outshines entire galaxies, making it visible across vast cosmic distances. The growth of TON-618 is further fueled by its environment. Located in a region rich with gas and other matter, the quasar has an abundant supply of material to feed upon. As the black hole grows more massive, its gravitational influence expands, allowing it to capture and consume even more distant matter, perpetuating a cycle of growth and energy release. Interestingly, The intense radiation and powerful jets emitted by TON-618 can also trigger star formation in its host galaxy, potentially providing even more fuel for future consumption. This complex interplay between the supermassive black hole and its galactic environment showcases the intricate and dynamic nature of cosmic evolution on the grandest scales. TON-618, the hypermassive black hole at the center of a distant quasar, is growing at an astonishing rate. This cosmic behemoth is consuming matter equivalent to about 65 suns every single day. Its voracious appetite makes it one of the fastest-growing black holes ever observed. The rapid growth of TON-618 is fueled by an immense accretion disk, a swirling vortex of gas and dust that surrounds the black hole. As this material spirals inward, it heats up to extreme temperatures, emitting enormous amounts of energy and making the quasar one of the brightest objects in the known universe. This extraordinary growth rate is not expected to continue indefinitely. Eventually, TON-618 will consume most of the readily available matter in its vicinity, slowing its expansion. However, given its current size and the vast amounts of material still within its gravitational influence, this black hole could continue growing for millions or even billions of years to come. The study of objects like TON-618 provides valuable insights into the formation and evolution of supermassive black holes and their host galaxies, helping scientists better understand the dynamics of our cosmic environment. Supermassive black holes like TON-618 face several constraints that limit their growth rate. One key factor is the availability of matter to consume. These cosmic giants require vast amounts of gas and dust to fuel their expansion, but the supply in their host galaxies is not infinite. As they devour the surrounding material, they can create powerful outflows that push remaining matter away, effectively limiting their own food supply. Another crucial limitation is the Eddington limit, which represents a balance between the outward pressure of radiation and the inward pull of gravity. When a black hole feeds too rapidly, it generates intense radiation that can repel incoming matter. This self-regulation mechanism prevents runaway growth and helps explain why we don't see even more massive black holes in the universe. Time also plays a significant role in limiting black hole growth. Even with optimal feeding conditions, it takes billions of years for these cosmic behemoths to reach such enormous sizes. The age of the universe itself sets an upper bound on how large they can become within the cosmic timescale available to them. Lastly, galaxy mergers and interactions influence supermassive black hole growth. While these events can provide fresh material for black holes to consume, they can also disrupt the steady accretion process. The complex dynamics of galactic collisions can alternately boost or hinder a black hole's growth rate, adding another layer of limitation to their expansion. The formation of TON-618, one of the most massive known black holes in the universe, remains a subject of intense scientific investigation. While the exact origins of this supermassive behemoth are not fully understood, the merger of smaller black holes is indeed one possible scenario that astronomers consider. Black hole mergers are known to occur throughout the cosmos, and they play a crucial role in the growth and evolution of these enigmatic objects. When two black holes collide and merge, they combine their masses and form a larger, more massive black hole. This process releases enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time that we can now detect with advanced instruments on Earth. However, the sheer size of TON-618 presents a challenge to this formation theory. With a mass estimated to be 66 billion times that of our Sun, it would require an extraordinary number of mergers to reach such proportions. Additionally, the age of the universe poses a constraint on how many mergers could have occurred within the available time frame. Another possibility is that TON-618 formed through a combination of mergers and rapid accretion of surrounding matter. This hybrid scenario suggests that the black hole may have started as a smaller seed, perhaps from the collapse of a massive star or the merger of several smaller black holes, and then grew rapidly by consuming vast amounts of gas and dust from its environment. This process, known as supermassive black hole feeding, could potentially explain the extreme mass of TON-618 while accounting for the time limitations imposed by the age of the universe. The supermassive black hole known as TON-618, currently the largest known black hole in the observable universe, presents a fascinating subject for future evolution. As it continues to consume surrounding matter, this cosmic behemoth is likely to grow even more massive over time. However, its growth rate may slow as it depletes the available material in its vicinity. The intense radiation emitted by the accretion disk surrounding TON-618 could potentially influence the formation and evolution of nearby galaxies. This radiation might inhibit star formation in its host galaxy, while simultaneously triggering star birth in more distant regions through compression of gas clouds. Over extremely long timescales, TON-618 might merge with other black holes, leading to an even more massive object. Such mergers would release enormous amounts of gravitational waves detectable by future, more sensitive instruments. The ultimate fate of TON-618, like all black holes, is tied to the fate of the universe itself. If current models of cosmic evolution hold true, it may eventually evaporate through Hawking radiation, but this process would take an almost unimaginably long time, far exceeding the current age of the universe. Dark matter likely played a crucial role in the growth of TON-618, the most massive known black hole in the universe. This supermassive behemoth, with a mass of 66 billion times that of our Sun, presents a fascinating puzzle for astronomers and cosmologists. The presence of dark matter in the early universe would have created deep gravitational wells, acting as cosmic scaffolding. These areas of intense gravity could have drawn in vast amounts of normal matter, creating the perfect conditions for the formation of massive black hole seeds. As these seeds grew, they would have continued to attract both dark and normal matter, fueling their rapid expansion. For a black hole to reach the extraordinary size of TON-618, it would need an enormous amount of matter to consume. Dark matter halos surrounding the forming galaxy could have channeled gas and dust toward the central region, providing a constant supply of fuel for the growing black hole. This process would have been particularly efficient in the early universe when matter was more densely packed. Furthermore, dark matter might have played a role in mergers between galaxies and their central black holes. These cosmic collisions, guided by the gravitational influence of dark matter, could have contributed to the rapid growth of TON-618, allowing it to reach its current mind-boggling proportions. TON-618 stands out as an extraordinary cosmic behemoth, growing at a rate that dwarfs most other supermassive black holes in the observable universe. This gargantuan black hole, located in a quasar more than 10 billion light-years away, is estimated to have a mass of 66 billion times that of our Sun, making it one of the most massive black holes ever discovered. The growth rate of TON-618 is truly staggering. It is believed to be accreting matter at a pace close to the theoretical maximum, known as the Eddington limit. This means it is consuming vast amounts of surrounding gas and dust, converting this material into energy with incredible efficiency. In comparison, most supermassive black holes in the present-day universe have much slower growth rates, often accreting matter at less than 1% of their theoretical maximum. What sets TON-618 apart is not just its size, but the era in which it achieved such enormous proportions. It reached its immense mass when the universe was less than 1 billion years old, a feat that challenges our understanding of black hole formation and growth. Most supermassive black holes take billions of years to reach masses of even a few billion solar masses, making TON-618 an exceptional case of rapid growth in the early universe. The extreme growth rate of TON-618 raises intriguing questions about the conditions in the early universe that could have fostered such rapid black hole expansion. It suggests that some regions of the cosmos may have been particularly conducive to black hole growth, with abundant gas and dust to fuel their development. Understanding the growth of objects like TON-618 could provide crucial insights into the formation of large-scale structures in the universe and the evolution of galaxies. TON-618, a supermassive black hole of staggering proportions, offers us a unique window into the conditions of the early universe. This cosmic behemoth, with a mass estimated at 66 billion times that of our Sun, challenges our understanding of black hole formation and growth. The existence of such an enormous black hole so early in cosmic history suggests that the seeds of these objects must have formed very quickly after the Big Bang. This rapid growth implies that the early universe was a place of intense activity, with vast amounts of matter available for these cosmic giants to consume. TON-618 size also indicates that the processes governing black hole growth in the early universe might have been different from what we observe today. It's possible that these ancient black holes had access to more efficient feeding mechanisms, allowing them to grow at rates that would be considered extreme by current standards. Furthermore, the presence of such massive black holes in the early universe could have played a crucial role in shaping the large-scale structure we see today. They may have influenced the formation of galaxies and clusters, acting as gravitational anchors around which cosmic structures coalesced. Thus, TON-618 not only tells us about black hole evolution, but also provides clues about the broader cosmic landscape in the universe's infancy. TON-618, the most massive known black hole in the observable universe, exerts an enormous influence on its surrounding galaxy. As this supermassive black hole continues to grow and evolve, its effects on the host galaxy will become increasingly pronounced. Over time, TON-618 will likely consume vast amounts of nearby gas and dust, reducing the available material for star formation. This process, known as quenching, could gradually transform the galaxy from a vibrant star-forming region into a more quiescent elliptical galaxy with fewer young stars. The immense gravitational pull of TON-618 will also shape the galaxy's structure. It may cause the galactic core to become more densely packed with stars, while simultaneously flinging other stars and gas to the outer regions of the galaxy or even into intergalactic space. This redistribution of matter could result in a more spheroidal galaxy shape, characteristic of massive elliptical galaxies. Furthermore, as TON-618 continues to accrete matter, it may periodically enter phases of intense activity, producing powerful jets of radiation and particles. These outflows could heat the surrounding gas, further suppressing star formation and potentially triggering galactic winds that expel material from the galaxy. The cumulative effect of these processes over billions of years could leave the host galaxy of TON-618 as a massive but largely dormant cosmic giant. Current theoretical models attempting to explain the existence of TON-618, the most massive known black hole in the universe, focus on several key concepts in astrophysics and cosmology. One prominent theory suggests that TON-618 formed through the repeated merging of smaller black holes over billions of years. This process, known as hierarchical merging, could have allowed the black hole to grow to its enormous size. Another model proposes that TON-618 might have formed from the direct collapse of a massive cloud of primordial gas in the early universe. This theory suggests that under certain conditions, a gas cloud could bypass the usual star formation process and collapse directly into a supermassive black hole. Some scientists also speculate that TON-618 could be the result of exotic physics or unknown phenomena. One such idea is the concept of primordial black holes, which might have formed in the extreme conditions of the very early universe, providing a seed for later growth. These models are not mutually exclusive, and the true origin of TON-618 might involve a combination of these processes or even mechanisms we have yet to discover. As our understanding of the universe expands, so too does our ability to explain such extraordinary cosmic objects. The immense size of TON-618, one of the largest known supermassive black holes in the observable universe, challenges our current models of black hole formation and growth. To account for its staggering mass, estimated at 66 billion times that of our Sun, scientists have proposed several theories. One possibility is that TON-618 formed from the merger of multiple smaller black holes over time. As galaxies collided and merged in the early universe, their central black holes could have coalesced, rapidly building up to the extraordinary mass we observe today. This process, however, would need to have occurred at an unprecedented rate to explain TON-618's size. Another theory suggests that TON-618 may have formed from the direct collapse of a massive cloud of primordial gas in the early universe. This scenario bypasses the usual stellar evolution process and allows for the rapid formation of a very massive seed black hole, which could then grow quickly through accretion. Some researchers propose that our understanding of black hole growth limits may need revision. TON-618's existence might indicate that black holes can accrete matter at rates higher than previously thought possible, or that they can sustain such growth for longer periods. This challenges our current models and pushes scientists to re-examine the physics of extreme gravitational environments. Cosmological models of the early universe make several key assumptions based on our current understanding of physics and observations. These models typically start with the idea that the universe began in an extremely hot, dense state known as the Big Bang. They assume that the fundamental laws of physics we observe today were also applicable in the early universe, though under much more extreme conditions. One crucial assumption is the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. This means that the distribution of matter and energy is roughly uniform across vast distances, and the universe looks the same in all directions. This assumption simplifies calculations and aligns with observations of the cosmic microwave background radiation. Another important assumption is that the early universe underwent a period of rapid expansion called cosmic inflation. This concept helps explain the uniformity of the cosmic microwave background and resolves several cosmological puzzles. Models also assume the existence of dark matter and dark energy, which are necessary to explain the observed structure and expansion of the universe. These models often rely on the standard model of particle physics, assuming that the fundamental particles and forces we know today emerged as the universe cooled and expanded. However, scientists recognize that our current theories may break down at the extreme energies and densities of the very early universe, leading to ongoing research into more comprehensive theories like quantum gravity. Theories about primordial black holes and the supermassive black hole TON-618 represent two extremes in the spectrum of black hole formation and growth. Primordial black holes are thought to have formed in the earliest moments of the universe, potentially emerging from density fluctuations during the inflationary period. These ancient black holes could range from microscopic sizes to masses comparable to small stars. TON-618, on the other hand, is a behemoth. It is one of the most massive known black holes in the observable universe, with an estimated mass of 66 billion times that of our Sun. This colossal object resides at the center of a distant quasar, over 10 billion light-years away from Earth. The sheer size of TON-618 challenges our understanding of black hole formation and growth processes. The connection between primordial black holes and TON-618 lies in the question of how such enormous black holes could form so early in the universe's history. Some theories suggest that primordial black holes could have served as seeds for the growth of supermassive black holes like TON-618. These early black holes might have rapidly accreted matter in the dense early universe, growing to extraordinary sizes over billions of years. However, the growth rate required for a primordial black hole to reach the mass of TON-618 would be exceptionally high. This has led scientists to explore alternative theories, such as the direct collapse of massive gas clouds or the merging of multiple black holes. The relationship between primordial black holes and objects like TON-618 remains an active area of research, pushing the boundaries of our understanding of cosmic evolution and the nature of these enigmatic objects. TON-618, the most massive known black hole in the observable universe, challenges our understanding of cosmic structures and their formation. Exotic matter, a hypothetical form of matter with properties that differ from conventional matter, could play a significant role in explaining the extreme nature of this supermassive black hole. Some theories suggest that exotic matter might have been present in the early universe, potentially contributing to the rapid growth of primordial black holes. In the case of TON-618, exotic matter could have provided an additional source of mass or energy, allowing the black hole to grow to its enormous size more quickly than current models predict. Another possibility is that exotic matter might alter the physics around extremely massive black holes like TON-618. This could affect the way the black hole interacts with its surroundings, potentially explaining some of its unusual characteristics or helping to stabilize such a massive object. However, it is important to note that the role of exotic matter in the formation and behavior of supermassive black holes remains highly speculative. Scientists continue to explore various theories to explain the existence of objects like TON-618, and the potential involvement of exotic matter represents just one avenue of investigation in this complex field of study. Models of TON-618, an ultramassive black hole, rely heavily on concepts from general relativity to accurately describe its extreme properties. General relativity, Einstein's groundbreaking theory of gravity, becomes crucial when dealing with objects of such immense mass and density. In these models, space-time itself is warped and curved to an extraordinary degree around TON-618. The intense gravitational field of this supermassive black hole causes time dilation effects, where time passes more slowly closer to the black hole compared to regions farther away. This time dilation must be accounted for in any calculations or simulations involving the black hole and its surroundings. The models also incorporate the concept of an event horizon, a boundary beyond which nothing can escape the black hole's gravitational pull. For TON-618, this event horizon is believed to be exceptionally large due to its enormous mass. The shape and behavior of this event horizon are described using equations derived from general relativity. Furthermore, these models consider how TON-618 affects the surrounding space, including the accretion disk of material swirling around it and the jets of particles ejected from its poles. General relativity helps explain how the intense gravity and rotation of the black hole influence these structures and the light emitted from the surrounding region. Cosmological models make several testable predictions about the nature and behavior of the universe. One key prediction is the existence of cosmic microwave background radiation, a faint glow of light that fills the entire sky, left over from the early stages of the universe. This radiation was indeed discovered and continues to be studied in great detail, providing strong support for the Big Bang theory. Another testable prediction is the abundance of light elements in the universe, such as hydrogen and helium. The Big Bang model predicts specific ratios of these elements, which closely match observations made by astronomers. Additionally, these models predict the large-scale structure of the universe, including the formation and distribution of galaxies and galaxy clusters. Advanced sky surveys have confirmed many of these predictions. Inflationary models of the early universe predict certain patterns in the cosmic microwave background, including specific types of temperature fluctuations. Ongoing and future missions aim to detect these patterns with increasing precision. Furthermore, some models predict the existence of gravitational waves from the early universe, which could potentially be detected by next-generation gravitational wave observatories. String theory, a complex framework in theoretical physics, could offer intriguing insights into the nature of TON-618, one of the most massive known black holes in the universe. This supermassive behemoth, located billions of light-years from Earth, challenges our current understanding of black hole formation and growth. At its core, string theory proposes that the fundamental constituents of the universe are tiny, vibrating strings of energy, rather than point-like particles. This concept could potentially explain how a black hole as enormous as TON-618 came into existence. String theory suggests that our universe might be one of many in a vast multiverse, and it is possible that TON-618 formed through the collision or merger of multiple universes. Furthermore, string theory introduces the idea of extra dimensions beyond the four we experience in everyday life. These additional dimensions might play a role in the extreme gravity and space-time curvature observed around TON-618. The theory could help scientists model how matter behaves in such intense gravitational fields, potentially revealing new insights about the internal structure and evolution of supermassive black holes. String theory also offers a potential resolution to the information paradox, a long-standing puzzle in black hole physics. This could be particularly relevant for TON-618, as its immense size amplifies questions about what happens to information that falls into a black hole. By providing a quantum description of gravity, string theory might help reconcile the apparent loss of information in black holes with the fundamental principles of quantum mechanics, shedding new light on the nature of these cosmic giants. TON-618 presents a significant challenge to our current understanding of supermassive black holes and their formation. This ultramassive black hole, located billions of light-years away, is estimated to have a mass of 66 billion times that of our Sun. This extraordinary size pushes the boundaries of existing models for black hole growth and evolution. One major limitation of current models is explaining how such an enormous black hole could form so early in the universe's history. Traditional theories suggest that black holes grow gradually by accreting matter and merging with other black holes over billions of years. However, TON-618 seems to have reached its immense size much faster than these models predict, calling into question our understanding of early universe conditions and black hole formation mechanisms. Another challenge lies in reconciling TON-618's mass with the size of its host galaxy. Typically, there's a correlation between the mass of a supermassive black hole and the mass of its host galaxy's central bulge. TON-618 appears to be far more massive than this relationship would suggest, indicating that our models of galaxy-black hole coevolution may be incomplete. Furthermore, current accretion models struggle to explain how TON-618 can maintain its extreme luminosity. The sheer amount of matter required to fuel such a massive black hole challenges our understanding of accretion physics and the mechanisms that regulate the growth of these cosmic giants. As we continue to study objects like TON-618, we're compelled to refine and potentially revolutionize our models of black hole formation and growth in the early universe. Our understanding of TON-618, the ultramassive black hole at the center of a distant quasar, continues to evolve as our knowledge of physics expands. Future advancements in physics could significantly enhance our models of this cosmic behemoth in several ways. Improved quantum gravity theories might provide deeper insights into the extreme conditions near TON-618's event horizon. These theories could help us better understand how space and time behave in the presence of such immense gravitational forces, potentially revealing new aspects of black hole physics we have yet to consider. Advancements in our understanding of dark matter and dark energy could also refine our models of TON-618's formation and growth. As we unravel the mysteries of these elusive components of the universe, we may gain new perspectives on how supermassive black holes accumulate mass over cosmic timescales. Furthermore, breakthroughs in plasma physics and magnetohydrodynamics could enhance our comprehension of the accretion processes fueling TON-618. This could lead to more accurate models of the quasar's energy output and the complex interactions between the black hole and its surrounding matter. TON-618, a hyperluminous quasar, presents significant challenges to our understanding of the early universe and galaxy formation. This cosmic behemoth houses an ultramassive black hole at its core, estimated to be 66 billion times more massive than our Sun. Such an enormous black hole existing in the distant past of our universe raises questions about how these cosmic giants could form and grow so quickly. Current models of galaxy and black hole formation struggle to explain the rapid growth required for TON-618 to reach its staggering size. The quasar's existence suggests that either our understanding of black hole growth mechanisms is incomplete, or that the seeds of these cosmic monsters were far larger than previously thought. The immense energy output of TON-618 also pushes the boundaries of our models for quasar physics. Its extreme luminosity, powered by the intense gravitational forces of its central black hole, challenges our theories about the limits of energy production in these cosmic powerhouses. Furthermore, the presence of such a massive object in the early universe forces us to reconsider our timeline of cosmic structure formation. It implies that the processes leading to the birth of supermassive black holes and their host galaxies may have occurred much faster than our current models predict, potentially requiring a revision of our understanding of the universe's early history. TON-618, a hyperluminous quasar discovered in the 1970s, offers us remarkable insights into the early universe. This celestial behemoth houses one of the most massive black holes ever detected, with an estimated mass of 66 billion times that of our Sun. Its existence challenges our understanding of how quickly supermassive black holes can form and grow in the cosmos. The presence of such an enormous black hole so early in the universe's history suggests that the processes of galaxy and black hole formation might have been more rapid and intense than previously thought. TON-618 formed when the universe was less than 1 billion years old, indicating that the conditions in the early universe were conducive to the rapid growth of these cosmic giants. This quasar also sheds light on the process of reionization, a crucial phase in the universe's evolution. During this period, the first stars and galaxies ionized the neutral hydrogen that pervaded space, making it transparent to ultraviolet light. The intense radiation from TON-618 and other early quasars likely played a significant role in this process, helping to shape the universe we observe today. Furthermore, the study of TON-618 and similar objects provides valuable data on the distribution of matter in the early universe, offering clues about the formation of large-scale structures we see in the present-day cosmos. Its existence pushes the boundaries of our theoretical models, prompting scientists to refine their understanding of black hole physics and galaxy evolution in the primordial universe. TON-618, the most massive known black hole in the observable universe, challenges our current models of galaxy formation and evolution. This ultra-massive black hole, with a mass equivalent to 66 billion suns, resides at the center of a quasar that existed when the universe was less than 1 billion years old. Its immense size and early formation raise questions about how such massive objects could grow so quickly in the young universe. Traditional theories suggest that galaxies form first, with black holes growing gradually at their centers. However, TON-618 implies that some supermassive black holes might have formed very early, potentially influencing or even driving the formation of their host galaxies. This could mean that in some cases, the central black hole plays a more active role in shaping galactic structure than previously thought. The existence of TON-618 also pushes the limits of our understanding of black hole growth mechanisms. It suggests that there might be more efficient ways for black holes to accumulate mass rapidly, such as through the direct collapse of massive gas clouds or the merging of multiple black holes. These possibilities require us to reconsider the conditions present in the early universe and how they might have facilitated such extreme growth. Furthermore, TON-618's impact extends beyond its immediate vicinity. Its powerful gravitational influence and intense radiation output likely affected the surrounding intergalactic medium, potentially altering the formation and evolution of nearby galaxies. By studying this cosmic behemoth and others like it, we can gain new insights into the complex interplay between supermassive black holes and the galaxies they inhabit, refining our understanding of cosmic structure formation on the largest scales. TON-618, the most massive known black hole in the observable universe, challenges our understanding of cosmic inflation and early universe formation. This ultramassive black hole, with a mass of approximately 66 billion times that of our Sun, existed when the universe was less than 1 billion years old. Its presence so early in cosmic history raises questions about how such enormous structures could form so quickly after the Big Bang. Cosmic inflation theory proposes that the universe underwent a period of rapid expansion in its first fraction of a second, creating the large-scale structure we observe today. The existence of TON-618 suggests that either inflation produced larger density fluctuations than previously thought, or that black holes can grow much faster than current models predict. This supermassive object also hints at the possibility of direct collapse black holes, which could have formed from the rapid infall of enormous gas clouds in the early universe. If this is the case, it might require modifications to our models of how the first stars and galaxies formed. The implications of TON-618 extend beyond black hole physics, potentially affecting our understanding of dark matter distribution, galaxy formation, and the overall evolution of the universe. As we continue to study this cosmic behemoth, it may lead to refinements or even significant revisions in the theory of cosmic inflation and our models of early universe dynamics. TON-618, the most massive known black hole in the observable universe, has significant implications for our understanding of cosmic structures and the total mass of the universe. This supermassive black hole, located in a quasar more than 10 billion light-years away, is estimated to have a mass of 66 billion times that of our Sun. Its existence challenges our previous models of black hole formation and growth. The discovery of such an enormous black hole forces astronomers to reconsider the upper limits of black hole masses in the universe. If objects like TON-618 are more common than previously thought, it could mean that a larger portion of the universe's mass is concentrated in supermassive black holes. This would affect our calculations of the universe's total mass, potentially increasing the estimate. Furthermore, the presence of TON-618 and other extremely massive black holes influences our understanding of galaxy formation and evolution. These cosmic giants likely play a crucial role in shaping the large-scale structure of the universe, affecting the distribution of matter across cosmic distances. As a result, they impact our models of how mass is distributed throughout the cosmos. While TON-618 alone does not drastically alter our overall estimate of the universe's mass, it represents a class of objects that, collectively, could lead to significant revisions in our understanding. As we continue to discover and study more supermassive black holes, we may need to adjust our calculations of cosmic mass distribution, dark matter content, and the overall composition of the universe. TON-618 offers us a remarkable glimpse into the extreme nature of supermassive black holes and their role in shaping the universe. This ultramassive black hole, located in a quasar more than 10 billion light-years away, is one of the largest known black holes in the observable universe. Its staggering mass, estimated at 66 billion times that of our Sun, challenges our understanding of how such enormous objects can form. The existence of TON-618 provides valuable insights into the distribution of matter in the early universe. Its immense size suggests that the cosmic environment in which it formed must have been exceptionally dense with gas and other matter. This indicates that certain regions of the early universe likely had significantly higher concentrations of matter than others, supporting theories of cosmic structure formation. Furthermore, TON-618 helps us understand the role of quasars in the evolution of galaxies. Quasars like the one hosting TON-618 are thought to have played a crucial part in regulating star formation and galactic growth through their powerful energy outputs. The presence of such a massive black hole so early in cosmic history implies that these processes began sooner and occurred more rapidly than previously believed. By studying objects like TON-618, astronomers can refine models of how matter was distributed in the early universe and how it has evolved over billions of years to form the cosmic structures we observe today. This knowledge is crucial for our understanding of the universe's overall composition and the forces that have shaped it throughout its history. TON-618, the most massive known black hole in the observable universe, challenges our understanding of cosmic structures and forces, including dark energy. This supermassive giant, with a mass equivalent to 66 billion suns, pushes the boundaries of what we thought possible for black hole growth. The existence of such an enormous black hole so early in the universe's history raises questions about the role of dark energy in cosmic evolution. Dark energy, the mysterious force causing the universe's accelerating expansion, might have influenced the formation and growth of these cosmic behemoths. By studying TON-618 and similar ultramassive black holes, scientists can refine models of how dark energy interacts with matter on the grandest scales. Furthermore, the gravitational effects of TON-618 on its surrounding space could provide a unique laboratory for testing theories of dark energy. The intense warping of space-time near such a massive object might reveal subtle effects of dark energy that are not observable in less extreme environments. As we continue to observe and analyze TON-618, we may uncover new insights into the interplay between dark energy, gravity, and the formation of cosmic structures. This could lead to a more comprehensive understanding of the forces shaping our universe and potentially reveal new aspects of dark energy's nature and behavior. TON-618, the most massive known black hole in the observable universe, provides fascinating insights into cosmic evolution and the potential destiny of our universe. This supermassive giant, with a mass equivalent to 66 billion suns, challenges our understanding of black hole formation and growth. The existence of such an enormous black hole suggests that the universe might be home to even larger cosmic titans, potentially hidden from our current detection methods. As these behemoths continue to consume matter and merge with other black holes, they could grow to truly staggering proportions over billions of years. This process of continuous growth and merging raises intriguing questions about the far future of the cosmos. If expansion continues indefinitely, these ultramassive black holes might become isolated islands in an ever-expanding void. However, if the universe eventually begins to contract, these giants could play a crucial role in the final stages of cosmic evolution. In a contracting universe scenario, TON-618 and its colossal cousins might ultimately combine into a single, unimaginably massive black hole. This could lead to a state where all matter and energy in the universe are concentrated into one point, potentially setting the stage for a new Big Bang and the birth of a new universe. Thus, TON-618 not only showcases the extremes of our current cosmos, but also hints at the cyclical nature of universal death and rebirth. TON-618, a hyperluminous quasar, challenges our understanding of cosmic structure formation in several ways. This extraordinary object, powered by an ultramassive black hole, pushes the boundaries of what we thought possible in the early universe. The sheer size of the black hole at the heart of TON-618, estimated to be 66 billion times the mass of our Sun, raises questions about how such massive objects could form so quickly after the Big Bang. Traditional models of black hole growth struggle to explain the existence of such enormous black holes in the distant past, forcing astronomers to reconsider the mechanisms of early galaxy and black hole formation. Furthermore, the intense radiation emitted by TON-618 would have had a significant impact on its surrounding environment. This powerful output could have influenced the formation and evolution of nearby galaxies, potentially altering the cosmic web of structure in its vicinity. Studying objects like TON-618 helps scientists refine models of how radiation from active galactic nuclei affects galaxy formation and the intergalactic medium. The existence of TON-618 also provides valuable insights into the relationship between supermassive black holes and their host galaxies. Understanding how such an enormous black hole coexists with its galaxy challenges our theories about the coevolution of black holes and galaxies, prompting new research into the complex feedback mechanisms that govern these relationships. TON-618, a hyperluminous quasar, stands as one of the most massive known black holes in the observable universe. Its colossal size and extreme brightness make it a prime target for future cosmological research, offering scientists a unique laboratory to study the physics of supermassive black holes and their effects on surrounding space. As our observational technologies advance, TON-618 could provide crucial insights into the formation and evolution of the largest cosmic structures. Its immense gravitational influence on nearby galaxies and intergalactic matter could help researchers better understand the role of supermassive black holes in shaping galactic neighborhoods and the broader cosmic web. Furthermore, TON-618's intense radiation output across multiple wavelengths presents an opportunity to study the extreme conditions near the event horizon of a truly gargantuan black hole. This could lead to refinements in our understanding of general relativity and potentially reveal new physics in these extreme gravitational environments. The quasar's great distance also makes it a valuable probe of the early universe. By studying the light from TON-618, astronomers can gain information about the intergalactic medium and the process of cosmic reionization, shedding light on the conditions present when the first stars and galaxies formed. TON-618 and the black hole at the center of M87 are both supermassive black holes, but they exist on vastly different scales. TON-618 is a true cosmic giant, dwarfing its counterpart in M87 by an enormous margin. While the M87 black hole is impressive in its own right, with a mass of about 6.5 billion times that of our Sun, TON-618 is in an entirely different league. The black hole at the heart of TON-618 is estimated to have a mass of 66 billion solar masses, making it one of the most massive black holes ever discovered. This means it is roughly 10 times more massive than the black hole in M87. To put this into perspective, if we were to replace our Sun with the black hole from M87, it would extend beyond the orbit of Neptune. However, if we were to do the same with TON-618, its event horizon would stretch far beyond our entire solar system. Another key difference between these two cosmic behemoths is their distance from Earth. The M87 black hole is relatively close, residing in a galaxy about 55 million light-years away. This proximity allowed scientists to capture its now famous image using the Event Horizon Telescope. TON-618, on the other hand, is much farther away, located approximately 10 billion light-years from Earth. The immense distance of TON-618 means we observe it as it appeared when the universe was much younger, providing a window into the early stages of galaxy and black hole formation. Despite its vast distance, the sheer size and brightness of TON-618 make it visible to us, highlighting the incredible power of these cosmic giants and their role in shaping the universe over billions of years. TON-618 and the black hole at the center of our Milky Way, known as Sagittarius A star, are both supermassive black holes, but their similarities largely end there. These cosmic giants share the fundamental properties of black holes, such as intense gravitational pull and the presence of an event horizon. However, the scale and environment of these two objects differ dramatically. The most striking contrast is their size. TON-618 is one of the largest known black holes in the universe, with a mass estimated to be 66 billion times that of our Sun. Sagittarius. A star, by comparison, is relatively modest, weighing in at about 4 million solar masses. This vast difference in scale means that TON-618 has a much larger event horizon and exerts a significantly stronger gravitational influence on its surroundings. Another key difference lies in their activity levels. TON-618 is classified as a quasar, meaning it is actively feeding on surrounding matter, causing it to emit enormous amounts of energy across the electromagnetic spectrum. Sagittarius A star, on the other hand, is currently in a quiescent state, accreting very little matter and producing relatively low levels of radiation. The environments surrounding these black holes also differ significantly. TON-618 resides in a distant galaxy billions of light-years away, while Sagittarius A star is much closer to home, allowing astronomers to study it in greater detail. Despite these differences, both black holes continue to fascinate scientists, offering valuable insights into the nature of these enigmatic cosmic objects and their role in galactic evolution. TON-618 stands out among ultramassive black holes due to its extraordinary size and mass. This cosmic behemoth is estimated to have a mass of 66 billion times that of our Sun, making it one of the most massive black holes ever discovered. To put this into perspective, TON-618 is about 10 times more massive than the largest black holes typically found at the centers of giant elliptical galaxies. What truly sets TON-618 apart is its classification as a hyperluminous quasar. It emits an enormous amount of energy, outshining entire galaxies. This intense luminosity is a result of the incredible amount of matter being consumed by the black hole, creating a bright accretion disk around it. The sheer scale of TON-618 challenges our understanding of black hole formation and growth. Its existence raises questions about how such a massive object could form so early in the universe's history. Scientists are still working to unravel the mysteries surrounding its origin and evolution. Furthermore, TON-618's immense gravitational influence likely extends far beyond what we typically see with other supermassive black holes. Its presence may have significantly shaped the structure and development of its host galaxy and the surrounding cosmic environment in ways we are still trying to comprehend. TON-618 is indeed a remarkable object, but it is not alone in challenging our understanding of black holes. Several other supermassive black holes have been discovered that push the boundaries of our current theories. One such example is the black hole at the center of galaxy NGC 1277. This black hole is exceptionally massive compared to the size of its host galaxy, making up about 17% of the galaxy's total mass. This proportion is far higher than what we typically observe in other galaxies, where the central black hole usually accounts for only 0.1% of the galaxy's mass. Another intriguing case is the ultramassive black hole in the galaxy Holmberg 15A. This black hole is estimated to have a mass of 40 billion times that of our Sun, making it one of the most massive black holes ever detected. Its enormous size challenges our understanding of how such massive black holes can form and grow. The black hole pair in the quasar OJ287 also presents a puzzle. These two supermassive black holes are on a collision course, spiraling towards each other in a cosmic dance that will eventually lead to their merger. This system provides a unique opportunity to study the dynamics of black hole mergers and their effects on surrounding spacetime. TON-618 stands out among ancient black holes due to its immense size and early formation in the universe's history. This supermassive black hole, located in a quasar more than 10 billion light-years away, is estimated to have formed when the universe was less than 1 billion years old. This places it among the earliest known supermassive black holes, challenging our understanding of how these cosmic giants came to be. Compared to other ancient black holes, TON-618 is exceptionally massive, weighing in at an estimated 66 billion times the mass of our Sun. This makes it one of the largest known black holes in the observable universe. Its rapid growth to such an enormous size so early in cosmic history presents a puzzle for astronomers and cosmologists. Most supermassive black holes are thought to have grown gradually over billions of years, accumulating mass as they consumed nearby stars and gas. However, TON-618 and other similarly ancient black holes seem to have reached their colossal sizes much more quickly. This suggests that there might be alternative formation mechanisms or growth processes that we do not yet fully understand. The existence of such massive black holes in the early universe has led scientists to propose new theories about rapid black hole formation and growth. These include the direct collapse of massive gas clouds or the merging of multiple smaller black holes. As we continue to study TON-618 and its ancient counterparts, we gain valuable insights into the conditions of the early universe and the processes that shaped the cosmic structures we see today. TON-618 stands out as one of the most extraordinary supermassive black holes ever discovered. Located billions of light-years from Earth, this cosmic giant dwarfs most other known black holes in sheer size and mass. Scientists estimate that TON-618 contains a staggering 66 billion times the mass of our Sun, making it one of the most massive black holes ever observed. The immense gravitational pull of TON-618 creates a vast accretion disk of superheated gas and dust swirling around it. This disk shines so brightly that it outshines entire galaxies, classifying TON-618 as an ultraluminous quasar. The energy output of this quasar is truly mind-boggling, releasing more energy every second than our Sun will emit in its entire lifetime. Another unique aspect of TON-618 is its rapid growth rate. Most supermassive black holes take billions of years to reach their enormous sizes, but TON-618 appears to have grown to its current proportions in a relatively short cosmic time frame. This rapid growth challenges our understanding of black hole formation and evolution, prompting scientists to reconsider existing theories. The extreme nature of TON-618 also provides a unique opportunity to study the limits of black hole physics. Its immense size and mass push the boundaries of our current models, allowing researchers to test theories about the maximum possible size of black holes and the effects of such massive objects on the surrounding space-time fabric. TON-618 stands out as one of the most extreme environments in the known universe. This ultramassive black hole dwarfs most others, with a mass estimated at 66 billion times that of our Sun. Its immense gravitational pull affects a vast region of space, creating a sphere of influence that extends far beyond what we typically see with other supermassive black holes. The area surrounding TON-618 is incredibly energetic. Its accretion disk, the swirling mass of superheated gas and dust being drawn into the black hole, shines with the brightness of hundreds of galaxies combined. This intense radiation would make the nearby space utterly inhospitable to life as we know it, with levels of high-energy particles and radiation far exceeding those found around smaller black holes. The jet streams emanating from TON-618 are also exceptionally powerful. These beams of particles, propelled to nearly the speed of light, extend for thousands of light-years into intergalactic space. They are capable of influencing the formation and evolution of galaxies across cosmic distances, a feature not seen to such an extent with less massive black holes. Compared to the environment around Sagittarius, a star, the supermassive black hole at the center of our Milky Way, The region around TON-618 is unimaginably more intense and chaotic. The sheer scale of its influence on its surroundings makes TON-618 a unique laboratory for studying extreme astrophysical phenomena and the upper limits of black hole growth in our universe. Comparing TON-618 to smaller supermassive black holes reveals fascinating insights into the extremes of cosmic phenomena. TON-618, an ultramassive black hole, is estimated to have a mass of 66 billion times that of our Sun, making it one of the largest known black holes in the universe. This colossal size dwarfs even the supermassive black holes found at the centers of most galaxies, including our own Milky Way's Sagittarius A star. The sheer scale of TON-618 challenges our understanding of black hole formation and growth. While smaller supermassive black holes are thought to have formed from the collapse of massive stars and grown over time by consuming matter and merging with other black holes. The existence of such an enormous entity as TON-618 suggests there might be alternative formation mechanisms at play. Some scientists propose that these ultramassive black holes could have formed directly from the collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. Studying TON-618 alongside smaller supermassive black holes also provides valuable information about the relationship between black holes and their host galaxies. Typically, there's a correlation between the mass of a supermassive black hole and the mass of its galaxy's central bulge. However, ultramassive black holes like TON-618 seem to break this rule, potentially indicating different evolutionary paths for these cosmic giants and their galactic homes. Furthermore, the comparison highlights the varying levels of activity in different-sized black holes. TON-618 powers an extremely luminous quasar, outshining entire galaxies, while many smaller supermassive black holes are relatively quiet. This contrast helps astronomers understand how black hole size relates to energy output and the impact these cosmic behemoths have on their surrounding space. TON-618 stands out as an extraordinary cosmic behemoth, even among the most massive black holes known to astronomers. This ultramassive black hole, located in a quasar more than 10 billion light-years away, is growing at a truly astonishing rate. Its growth outpaces that of nearly all other known supermassive black holes in the observable universe. While typical supermassive black holes in galactic centers might grow by accreting matter equivalent to 1 solar mass per year, TON-618 is estimated to be devouring matter at a rate hundreds of times faster. Some calculations suggest it could be consuming the equivalent of 600 solar masses of material each year, a rate that dwarfs the growth of other rapidly expanding black holes. This phenomenal growth rate raises intriguing questions about the mechanisms fueling such rapid expansion. Astronomers theorize that TON-618 might be situated in an environment exceptionally rich in gas and dust, providing an abundant cosmic buffet for its insatiable appetite. Additionally, its immense gravitational pull likely allows it to draw in material from a vast surrounding region, further accelerating its growth. The extreme nature of TON-618's growth challenges our understanding of black hole formation and evolution. It pushes the boundaries of what scientists thought possible in terms of black hole feeding rates and may require new models to fully explain its extraordinary development. As we continue to study this cosmic giant, it promises to reveal more secrets about the most extreme objects in our universe and the processes that shape galactic evolution on the grandest scales. Studying TON-618 alongside other extreme cosmic objects provides valuable insights into the limits of our universe. This ultramassive black hole, with a mass estimated at 66 billion times that of our Sun, pushes the boundaries of our understanding of how such enormous objects can form and evolve. By comparing TON-618 to other supermassive black holes, scientists can better grasp the mechanisms behind their growth. This comparison helps reveal whether there are upper limits to black hole masses and if different formation processes might be at play for the most extreme examples. The study of TON-618 also sheds light on the relationship between supermassive black holes and their host galaxies. Its extraordinary size challenges current models of galaxy formation and evolution, prompting researchers to refine their theories about how galaxies and their central black holes influence each other's growth. Furthermore, Examining TON-618 alongside other cosmic heavyweights like quasars and galaxy clusters allows scientists to piece together a more comprehensive picture of the early universe. This knowledge is crucial for understanding the cosmic web's structure and the role of dark matter and dark energy in shaping our universe over billions of years. TON-618 remains one of the most enigmatic objects in our known universe, presenting astronomers with several intriguing mysteries. This ultramassive black hole, located billions of light-years away, challenges our understanding of cosmic evolution and the limits of physics. One of the primary unanswered questions about TON-618 is how it grew to such an enormous size. With a mass estimated at 66 billion times that of our Sun, it far exceeds what current models predict for black hole growth. Scientists are puzzled by the mechanisms that could have allowed it to accumulate so much matter in the relatively short time since the Big Bang. Another key question concerns the impact of TON-618 on its host galaxy. Typically, supermassive black holes coexist with their galaxies in a delicate balance. However, the sheer size of TON-618 suggests it might dominate its galactic environment completely. Researchers are keen to understand how such a massive object affects star formation and galactic structure in its vicinity. The extreme nature of TON-618 also raises questions about the upper limits of black hole mass. Scientists wonder if there are even larger black holes lurking in the cosmos, and if so, what implications this might have for our understanding of galactic evolution and the early universe. These questions continue to drive research and fuel our fascination with this cosmic behemoth. The James Webb Space Telescope, with its advanced infrared capabilities, is poised to revolutionize our understanding of distant cosmic objects like TON-618. This extraordinary quasar, located over 10 billion light-years away, harbors one of the most massive black holes ever discovered. James Webb's powerful instruments can peer through cosmic dust and gas, allowing astronomers to observe TON-618 in unprecedented detail. By analyzing the infrared spectrum of the quasar, scientists can gain valuable insights into its composition, temperature, and the processes occurring near the supermassive black hole at its core. One of the most exciting prospects is the potential to study the host galaxy of TON-618. Previous telescopes have struggled to distinguish the faint galaxy from the brilliant quasar, but James Webb's superior resolution and sensitivity might finally reveal the galactic environment surrounding this cosmic giant. This could help scientists understand how such enormous black holes and their host galaxies co-evolved in the early universe. Furthermore, the telescope's ability to detect faint redshifted light from distant objects might allow astronomers to identify other quasars and supermassive black holes in the vicinity of TON-618. This could provide valuable context about the cosmic neighborhood of this extraordinary object and shed light on the formation and growth of the largest structures in the universe. To better understand TON-618, the most massive known black hole in the universe, several technological advancements are necessary. First and foremost, we need more powerful telescopes capable of peering deeper into space with greater clarity. These advanced instruments would allow astronomers to observe TON-618 and its surrounding environment in unprecedented detail. Improvements in spectroscopic technology are also crucial. Enhanced spectrographs could help scientists analyze the light emitted from the quasar surrounding TON-618 more precisely, providing valuable data about its composition, temperature, and behavior. This information would offer insights into the processes occurring near the event horizon of this supermassive black hole. Additionally, advancements in computer modeling and simulation capabilities are essential. More sophisticated algorithms and faster supercomputers would enable scientists to create more accurate models of TON-618 and its effects on nearby spacetime. These simulations could help test theories about the formation and evolution of such massive black holes. Lastly, progress in gravitational wave detection technology could potentially allow us to detect and study gravitational waves emanating from TON-618. This would provide a new avenue for understanding the dynamics of this cosmic giant and its interactions with surrounding matter and energy. Gravitational wave detectors could play a crucial role in studying TON-618, the most massive known black hole in the universe. These sophisticated instruments, designed to detect ripples in the fabric of spacetime, offer a unique way to observe and analyze this supermassive cosmic giant. TON-618, with its staggering mass of approximately 66 billion times that of our Sun, presents a remarkable opportunity for gravitational wave research. As objects of such immense mass interact with their surroundings, they generate powerful gravitational waves. These waves, predicted by Einstein's theory of general relativity, carry valuable information about the black hole and its environment. By using gravitational wave detectors to observe TON-618, scientists could potentially detect signals from smaller black holes or dense stars orbiting this behemoth. Such observations would provide unprecedented insights into the dynamics of extreme gravitational fields and the behavior of matter in the vicinity of supermassive black holes. Furthermore, gravitational wave data could help refine our understanding of TON-618's precise mass, spin, and other properties. This information would be invaluable for testing theories of black hole formation and evolution, especially for such extremely massive objects. The study of TON-618 through gravitational waves could thus open new frontiers in our exploration of the most extreme objects in the cosmos. Artificial intelligence could revolutionize our study of TON-618, the supermassive black hole that continues to captivate astronomers. As we delve deeper into the mysteries of this cosmic giant, AI systems could process and analyze vast amounts of observational data far more quickly and efficiently than human researchers alone. Advanced machine learning algorithms might detect subtle patterns in the radiation emitted from the accretion disk surrounding TON-618, potentially revealing new insights about its structure and behavior. These AI tools could also help simulate the extreme conditions near the black hole's event horizon, allowing scientists to test theories about gravity and spacetime in ways that were previously impossible. Furthermore, artificial intelligence could assist in the complex task of filtering out background noise and interference from our observations of TON-618. This would provide clearer, more accurate data for astronomers to work with, potentially leading to groundbreaking discoveries about the nature of supermassive black holes and their role in galactic evolution. As we continue to push the boundaries of our understanding of the universe, the partnership between human ingenuity and artificial intelligence will likely play a crucial role in unraveling the enigmas posed by cosmic behemoths like TON-618. Computer simulations play a crucial role in our study of distant cosmic objects like TON-618, the hyperluminous quasar that houses one of the most massive known black holes in the universe. As our technology advances, these simulations become more sophisticated, allowing us to delve deeper into the mysteries surrounding this extraordinary celestial body. Enhanced simulations could provide us with a more accurate model of TON-618's structure and behavior. They could help us better understand the intense gravitational forces at play around the supermassive black hole, as well as the complex interactions between the black hole and the surrounding matter. This would give us invaluable insights into how such enormous black holes form and evolve over cosmic timescales. Moreover, improved simulations could shed light on the mechanisms behind TON-618's incredible luminosity. By modeling the accretion disk and the powerful jets of radiation emitted by the quasar, we could gain a clearer picture of the extreme physics at work in these environments. This knowledge could potentially be applied to our understanding of other quasars and active galactic nuclei throughout the universe. Advanced simulations might also allow us to explore TON-618's impact on its host galaxy and the surrounding intergalactic medium. By modeling these interactions over millions or even billions of years, we could better comprehend how such massive black holes influence galactic evolution and cosmic structure formation on the largest scales. To unravel the enigmas surrounding TON-618, astronomers have proposed several intriguing experiments. One approach involves using advanced gravitational wave detectors to capture the ripples in spacetime caused by objects orbiting this supermassive black hole. By analyzing these waves, scientists could gain insights into the black hole's mass, spin, and even the structure of spacetime near its event horizon. Another potential experiment focuses on high-resolution imaging techniques. By combining data from multiple radio telescopes across the globe, researchers aim to create a virtual Earth-sized telescope. This method, known as Very Long Baseline Interferometry, could potentially produce the first direct image of TON-618's event horizon, similar to the groundbreaking image of the black hole in Messier 87. Spectroscopic studies offer another avenue for exploration. By carefully analyzing the light emitted from the region surrounding TON-618, scientists hope to determine the composition and motion of gas and dust in its accretion disk. This information could provide clues about the black hole's growth rate and the mechanisms that fuel its incredible luminosity. Lastly, long-term monitoring campaigns could reveal variations in TON-618's brightness and spectral features. These observations might uncover periodic patterns or unexpected changes, shedding light on the complex interplay between the black hole and its surrounding environment. Through these diverse approaches, astronomers aim to peel back the layers of mystery surrounding this cosmic giant. International collaboration could significantly accelerate research on TON-618, the supermassive black hole that holds the record for the most massive known black hole in the observable universe. By pooling resources, expertise, and observational data from multiple countries, scientists could gain deeper insights into this cosmic behemoth. Coordinated efforts between space agencies like NASA, ESA, and JAXA could lead to more comprehensive observations using a variety of telescopes and instruments. This multi-wavelength approach would provide a more complete picture of TON-618 and its surrounding environment. Additionally, shared supercomputing resources could enable more sophisticated simulations of the black hole's behavior and its effects on the surrounding galaxy. International partnerships could also facilitate the development of new technologies specifically designed to study extremely massive black holes. These might include advanced adaptive optics systems for ground-based telescopes or specialized space-based observatories. Such collaborations could potentially lead to breakthroughs in our understanding of how such enormous black holes form and evolve. Furthermore, a global network of researchers working on TON-618 would foster the exchange of ideas and methodologies, potentially leading to innovative approaches in studying supermassive black holes. This collective effort could not only advance our knowledge of TON-618, but also contribute to our broader understanding of the role of supermassive black holes in galactic evolution and the early universe. TON-618, the hyperluminous quasar at the heart of a distant galaxy, continues to intrigue astronomers and physicists alike. To unlock its secrets, scientists are turning to interdisciplinary approaches that combine multiple fields of study. Astrophysicists and cosmologists are collaborating with experts in fluid dynamics to better understand the complex interactions within the accretion disk surrounding TON-618's supermassive black hole. This partnership could reveal new insights into how such enormous black holes feed and grow to their staggering sizes. Another promising avenue involves the intersection of quantum mechanics and general relativity. Theoretical physicists are working alongside computer scientists to develop advanced simulations that might shed light on the extreme gravitational environment near TON-618's event horizon. These models could help explain the mechanisms behind the quasar's intense energy output. Astrochemists are also joining forces with spectroscopists to analyze the chemical composition of TON-618's surrounding region. By studying the quasar's spectral lines in unprecedented detail, they hope to uncover clues about the early universe and the formation of the first galaxies. This collaborative effort might even provide new information about the cosmic distribution of elements and the history of star formation. Studying TON-618, the most massive known black hole in the universe, offers a unique opportunity to push the boundaries of our understanding in various areas of physics. This supermassive black hole, with a mass estimated at 66 billion times that of our Sun, serves as an extreme laboratory for testing theories of gravity and the behavior of matter under intense conditions. By observing TON-618, scientists can gain insights into the formation and evolution of supermassive black holes, which in turn helps us understand the growth of galaxies and the large-scale structure of the universe. The immense gravitational pull of TON-618 also allows researchers to study the effects of extreme space-time curvature, potentially revealing new aspects of general relativity or even hinting at the need for modifications to our current gravitational theories. Furthermore, the study of TON-618 can contribute to our knowledge of accretion processes, the mechanisms by which black holes grow by consuming surrounding matter. This understanding has implications for various astrophysical phenomena, including the formation of jets and the emission of gravitational waves. The extreme environment around TON-618 also provides an opportunity to study plasma physics and magnetohydrodynamics under conditions impossible to replicate in Earth-based laboratories. Lastly, the existence of such a massive black hole challenges our current models of black hole growth and galaxy evolution. By studying TON-618, scientists may uncover new mechanisms for rapid black hole growth in the early universe, leading to advancements in our understanding of cosmology and the history of our universe. These insights could have far-reaching implications across multiple areas of physics, from quantum mechanics to particle physics, as we strive to reconcile our theories of the very large with those of the very small. TON-618 presents an intriguing yet challenging environment for potential life. This supermassive black hole, located billions of light-years from Earth, is one of the largest known black holes in the observable universe. Its immense gravitational pull affects everything in its vicinity, creating conditions vastly different from those we associate with life. The intense radiation and extreme gravitational forces near TON-618 would likely make it impossible for life as we know it to exist in its immediate surroundings. However, the regions farther from the black hole might offer more promising possibilities. In the outer reaches of the system, where the black hole's influence is less severe, there could be planets or moons with more stable conditions. These distant worlds might have the potential to harbor life forms adapted to their unique environment. Such organisms would need to evolve mechanisms to cope with higher levels of radiation and gravitational stress than those found on Earth. They might develop protective outer layers, efficient repair systems for radiation damage, or entirely novel biological processes we have yet to imagine. While the existence of life near TON-618 remains speculative, studying such extreme environments pushes the boundaries of our understanding. It challenges us to reconsider what conditions are truly necessary for life to emerge and thrive, expanding our search for extraterrestrial life beyond familiar cosmic neighborhoods. The environment around TON-618, the most massive known black hole in the observable universe, would present insurmountable challenges for life as we understand it. This supermassive black hole, with a mass of 66 billion times that of our Sun, creates an environment of unimaginable extremes. The intense gravitational forces near TON-618 would stretch and compress any matter, including potential life forms, in a process called spaghettification. This would tear apart even the most resilient organisms at the molecular level. The immense tidal forces would make it impossible for complex structures, let alone living beings, to maintain their integrity. Radiation levels around TON-618 would be lethal to any known form of life. The accretion disk, a swirling mass of superheated gas and dust falling into the black hole, emits enormous amounts of high-energy radiation across the electromagnetic spectrum. This includes X-rays and gamma rays, which would quickly destroy any organic molecules. Furthermore, the extreme temperatures in the vicinity of TON-618 would preclude the existence of liquid water, often considered essential for life. Near the event horizon, temperatures could reach millions of degrees, while further out, the intense radiation would still heat the surrounding space to levels far beyond the tolerance of any known organisms. These conditions make the area around TON-618 one of the most inhospitable environments imaginable, virtually eliminating the possibility of life as we know it. Black holes like TON-618, one of the most massive known supermassive black holes in the universe, represent an almost unimaginable source of energy. For advanced civilizations, tapping into this cosmic powerhouse could potentially provide energy on a scale far beyond anything we can currently conceive. One theoretical method for extracting energy from a black hole is the Penrose process, named after physicist Roger Penrose. This involves dropping objects into the ergosphere, a region just outside the event horizon where space itself is dragged along by the black hole's rotation. By splitting the object in two and allowing one half to fall into the black hole while the other escapes, it's possible to extract more energy than was initially input. Another possibility is the Blandford-Znajek process, which could allow civilizations to extract the rotational energy of a black hole through electromagnetic fields. This process is thought to be responsible for powering the jets we observe from some active galactic nuclei and quasars. However, harnessing the energy of a black hole as enormous as TON-618 would present immense engineering challenges. The gravitational forces and intense radiation near such a massive object would likely require technology far beyond our current capabilities. Yet for a sufficiently advanced civilization, the rewards could be astronomical, potentially providing enough energy to power entire galactic civilizations for eons. TON-618, a supermassive black hole of staggering proportions, exerts an enormous influence on its host galaxy. This cosmic behemoth, with a mass equivalent to 66 billion suns, creates an environment that could significantly impact the potential for life to emerge and thrive. The intense radiation emitted from the accretion disk surrounding TON-618 bathes its galaxy in high-energy particles. This constant bombardment might sterilize nearby planets, making it challenging for life as we know it to develop in the central regions of the galaxy. However, this same radiation could also trigger complex chemical reactions on distant worlds, potentially kickstarting the formation of organic compounds necessary for life. The immense gravitational pull of TON-618 affects star formation throughout its galaxy. It may disrupt molecular clouds, preventing some stars from forming, while simultaneously compressing others and triggering rapid star birth. This dynamic environment could lead to the creation of diverse planetary systems, some potentially suitable for life. Furthermore, the powerful jets emanating from TON-618 could spread heavy elements produced near the black hole across vast distances. These elements, crucial for the formation of planets and the chemistry of life, might seed far-flung regions of the galaxy with the building blocks necessary for biological processes to emerge. TON-618, the ultramassive black hole at the heart of a distant quasar, is a cosmic behemoth of staggering proportions. With a mass estimated at 66 billion times that of our Sun, it stands as one of the largest known black holes in the observable universe. This colossal object's immense gravitational pull causes it to consume vast amounts of matter, creating a brilliant quasar that outshines entire galaxies. The intense radiation emitted by TON-618 makes it visible across cosmic distances, potentially serving as a natural beacon in the vastness of space. Its consistent and powerful output could theoretically be used as a reference point for interstellar navigation or communication. Advanced civilizations might use such prominent cosmic objects to create a shared coordinate system for the galaxy, or even as a common reference in attempts to communicate across vast distances. However, using TON-618 for direct communication poses significant challenges. The extreme distances involved, measured in billions of light-years, mean that any signal sent using this quasar as a reference would take billions of years to reach its destination. Additionally, the intense radiation and gravitational forces surrounding the black hole would likely interfere with or destroy any artificial signals in its vicinity. While TON-618 may not be practical for direct communication, its existence and properties could still play a role in theoretical long-term interstellar communication strategies. Its visibility across vast cosmic distances makes it a potential universal reference point, akin to a cosmic lighthouse that could be recognized by any sufficiently advanced civilization in our universe. TON-618, a supermassive black hole of extraordinary size, dramatically alters the concept of habitable zones in its cosmic neighborhood. Its immense gravitational influence extends far beyond what we typically consider for stellar systems, creating an environment hostile to life as we know it. The sheer power of TON-618 warps space and time to such an extreme degree that traditional notions of planetary orbits become almost meaningless. Any planets that might exist in its vicinity would be subject to intense gravitational forces, likely resulting in highly elliptical or unstable orbits. This gravitational chaos would make it nearly impossible for a planet to maintain the consistent conditions necessary for life to develop and thrive. Moreover, TON-618 emits an enormous amount of energy in the form of radiation and high-energy particles. This intense radiation would sterilize any nearby planets, stripping away their atmospheres and bombarding their surfaces with lethal levels of cosmic rays. The concept of a habitable zone, typically defined as the region around a star where liquid water can exist on a planet's surface, becomes irrelevant in the face of such extreme conditions. The influence of TON-618 extends so far that it affects entire galaxies, not just individual star systems. Its presence likely disrupts star formation processes and alters the distribution of matter across vast cosmic distances. In this environment, the very building blocks of habitable planets may be scattered or destroyed before they can even begin to coalesce. Life near TON-618 would face extraordinary challenges due to the extreme environment created by this ultra-massive black hole. The immense gravitational forces would significantly impact any potential evolutionary processes. Organisms would need to adapt to withstand intense tidal forces that could tear apart larger life forms. This might lead to the evolution of smaller, more compact organisms with incredibly strong cellular structures. Radiation would be another major factor shaping life near TON-618. The accretion disk surrounding the black hole emits powerful X-rays and gamma rays, which would be lethal to most Earth-like organisms. Any life evolving in this environment would require advanced radiation shielding mechanisms, perhaps developing biological processes to repair DNA damage rapidly or using elements that are more resistant to ionizing radiation. The extreme energy output of TON-618 would create a unique light environment. With the black hole outshining entire galaxies, organisms might evolve highly specialized light-sensing organs to navigate and communicate in this perpetually bright realm. Alternatively, life could adapt to thrive in the shadows of celestial bodies, developing extraordinary sensitivities to minute changes in light and energy. Time dilation effects near the black hole could also influence evolution in unexpected ways. Organisms closer to TON-618 would experience time more slowly relative to those farther away. This could lead to divergent evolutionary paths, with species closer to the black hole evolving at different rates than their more distant counterparts. Such unique pressures could result in life forms and evolutionary strategies entirely unlike anything we have observed in our corner of the universe. TON-618, the most massive known black hole in the observable universe, offers intriguing possibilities for our search for extraterrestrial intelligence. This supermassive behemoth, with a mass equivalent to 66 billion suns, could serve as a cosmic beacon for advanced civilizations. Highly advanced alien societies might harness the immense energy output of such massive black holes using hypothetical megastructures like Dyson spheres. These constructions could capture and utilize the intense radiation emitted from the accretion disk surrounding TON-618. By searching for signs of artificial energy manipulation around this and other supermassive black holes, we might detect evidence of technological activity on an unimaginable scale. Furthermore, the extreme gravitational environment near TON-618 could provide unique conditions for testing fundamental physics. Advanced civilizations might use this natural laboratory to conduct experiments beyond our current capabilities. Detecting unusual phenomena or unexplained signals from the vicinity of TON-618 could indicate the presence of intelligent activity. Studying TON-618 and similar supermassive black holes might also reveal natural processes that could mimic signs of intelligence. This knowledge would help us refine our search criteria and avoid false positives in our quest for extraterrestrial life. By expanding our understanding of these cosmic giants, we enhance our ability to distinguish between natural phenomena and potential techno-signatures across the universe. The supermassive black hole known as TON-618, located billions of light-years from Earth, presents an intriguing possibility for preserving information about ancient civilizations, albeit in a way that challenges our understanding of physics and information theory. Black holes, including TON-618, which is one of the largest known black holes in the universe, have an event horizon beyond which nothing, not even light, can escape. This property led to a long-standing paradox in physics about whether information could truly be lost when it falls into a black hole. However, recent theories in quantum mechanics suggest that information might not be completely lost when it enters a black hole. Instead, it could be preserved on the event horizon as a form of holographic encoding. This concept, known as the holographic principle, proposes that all the information about objects that fall into a black hole might be retained on its two-dimensional surface. If these theories are correct, TON-618 could potentially hold vast amounts of information about ancient civilizations that may have existed in its vicinity over billions of years. However, even if this information is preserved, retrieving or decoding it remains far beyond our current technological capabilities and understanding of physics. The sheer size and distance of TON-618 make it an object of great scientific interest, but also immense practical challenges for any potential future exploration or study. The colossal black hole. TON-618 challenges our understanding of cosmic structures and their formation. Its immense size, estimated at 66 billion times the mass of our Sun, pushes the boundaries of what we thought possible in the early universe. This extreme object could inspire astrobiologists to reconsider the conditions necessary for life to emerge and evolve. The intense gravitational forces and radiation around TON-618 create environments unlike anything we observe in our galactic neighborhood. These extreme conditions might lead scientists to explore new chemical pathways for the formation of complex molecules, potentially expanding our definition of habitable zones. The powerful jets emanating from this supermassive black hole could seed vast regions of space with heavy elements, potentially kick-starting chemical processes conducive to life on a galactic scale. Furthermore, the existence of such a massive black hole so early in the universe's history suggests that cosmic structures can form and evolve much faster than previously thought. This rapid development could have implications for the timeline of potential life emergence in the cosmos, prompting astrobiologists to consider scenarios where biological processes might accelerate under extreme conditions. TON-618 also raises questions about the nature of galaxies and their central black holes. If life can exist in these extreme galactic environments, it might possess characteristics vastly different from Earth-based organisms, expanding our search criteria for extraterrestrial life and challenging our preconceptions about the limits of biology. The hypermassive black hole TON-618 has captured the imagination of science fiction writers and creators, serving as a source of inspiration for various stories and concepts. In science fiction literature, this colossal cosmic entity has been depicted as a gateway to other dimensions, a potential source of unlimited energy, and even as the home of advanced alien civilizations. Some narratives have explored the idea of future human expeditions venturing near TON-618, using its immense gravitational forces for faster-than-light travel or time manipulation. Other stories have imagined the black hole as a looming threat, with its massive size and power posing existential risks to entire galaxies. In visual media, TON-618 has been portrayed as an awe-inspiring spectacle, often shown as a massive, swirling vortex of light and energy against the backdrop of space. Its enormous accretion disk, which outshines entire galaxies, has been used to create stunning visuals in science fiction films and television shows. While these portrayals often take creative liberties with the scientific facts, they have helped to bring attention to this remarkable cosmic object and spark public interest in black hole research and astrophysics. The sheer scale and power of TON-618 continue to provide fertile ground for imaginative storytelling in the realm of science fiction. TON-618, the ultra-massive black hole at the center of a distant quasar, is often misrepresented in popular media. One common misconception is that it poses an immediate threat to Earth or our galaxy. In reality, TON-618 is located approximately 10 billion light-years away, far beyond any potential influence on our cosmic neighborhood. Another frequent error is the portrayal of TON-618 as a cosmic vacuum cleaner, constantly pulling in everything around it. While its gravitational influence is indeed enormous, black holes do not actively suck in matter from great distances. Objects need to cross the event horizon to be captured, and many stars and gas clouds can orbit a black hole stably for long periods. Media sometimes exaggerates the size of TON-618, claiming it dwarfs entire galaxies. Although it is incredibly massive, estimated at 66 billion times the mass of our Sun, it remains tiny compared to the vast expanses of its host galaxy. The event horizon, while large for a black hole, would still fit within our solar system. Lastly, there is often confusion about the nature of quasars like TON-618. They are frequently depicted as separate entities from black holes, when in fact a quasar is the incredibly bright region around an active supermassive black hole powered by the intense energy released as a matter falls into it. TON-618, the most massive known black hole in the observable universe, has captured the imagination of artists and creators across various media. This cosmic behemoth, with its staggering size and power, has become a source of inspiration for science fiction writers, visual artists, and musicians alike. In literature, authors have used TON-618 as a backdrop for epic space operas and mind-bending cosmic horror stories. Its immense gravitational pull and the extreme physics at play near its event horizon provide fertile ground for exploring themes of time dilation, reality warping, and the limits of human understanding. Visual artists have created stunning depictions of TON-618, often portraying it as a monstrous void surrounded by swirling galaxies and streams of matter. These artworks frequently emphasize the scale of the black hole, juxtaposing it with familiar objects to highlight its incomprehensible size. Digital artists and animators have also produced mesmerizing simulations of what it might look like to approach such a massive black hole, drawing on scientific models to create awe-inspiring visualizations. Musicians and composers have found inspiration in TON-618 as well, creating ambient soundscapes and electronic compositions that attempt to capture the sense of vastness and power associated with this cosmic giant. Some have even used mathematical models of black hole physics to generate unique sound patterns, translating the language of astrophysics into auditory experiences that evoke the mysteries of the cosmos. TON-618 serves as a remarkable example in educational outreach about supermassive black holes. This ultramassive black hole, located billions of light years away from Earth, captivates audiences with its extraordinary size and power. Scientists estimate its mass to be around 66 billion times that of our Sun, making it one of the largest known black holes in the observable universe. When educators and scientists discuss TON-618, they often use it to illustrate the upper limits of black hole growth. This cosmic behemoth helps learners grasp the incredible scale and diversity of black holes, ranging from stellar mass black holes to these gargantuan supermassive ones. TON-618 also provides a platform to explain complex concepts like quasars, as it resides at the center of an extremely luminous quasar. Furthermore, TON-618 sparks discussions about the formation and evolution of galaxies. Its immense size raises questions about how such massive black holes came to be and how they influence their host galaxies. This leads to conversations about cosmic evolution, the early universe, and the intricate relationship between black holes and galactic structures. By showcasing TON-618, educators can inspire awe and curiosity about the cosmos, encouraging students and the public to delve deeper into astrophysics and cosmology. Its extreme nature makes it a powerful tool for demonstrating the dynamic and often surprising nature of our universe, helping to ignite a passion for space science in learners of all ages. TON-618, the colossal supermassive black hole at the heart of a distant quasar, has captured public imagination through the power of social media. This astronomical behemoth, estimated to be 66 billion times more massive than our Sun, has become a subject of fascination for space enthusiasts and casual observers alike. Social media platforms have played a crucial role in spreading awareness about TON-618. Striking visual representations, often created by talented artists and shared widely on platforms like Instagram and Twitter, have helped people visualize the sheer scale of this cosmic giant. These images, comparing TON-618 to other known black holes or even entire galaxies, have gone viral, reaching millions of users who might otherwise never have encountered such astronomical concepts. Moreover, science communicators and educators have leveraged social media to explain the significance of TON-618 in accessible terms. Short video clips, infographics, and bite-sized facts about this supermassive black hole have proliferated across platforms like TikTok and YouTube, making complex astrophysical concepts more digestible for the general public. This has led to increased engagement with space science topics and sparked curiosity about the nature of black holes and the structure of our universe. The viral nature of social media has also encouraged broader discussions about TON-618 and its implications for our understanding of cosmic evolution. As users share and comment on posts related to this enormous black hole, they often pose questions that lead to further exploration of astrophysics and cosmology, fostering a cycle of learning and discovery that extends far beyond traditional educational settings. To grasp the immense scale of TON-618, astronomers often employ relatable analogies. One common comparison is to our own Milky Way galaxy. TON-618's supermassive black hole is estimated to be about 66 billion times the mass of our Sun, while the entire Milky Way galaxy weighs approximately 1 trillion solar masses. This means the black hole alone is about 6% of our galaxy's total mass, a staggering proportion that challenges our understanding of cosmic structures. Another analogy uses our solar system for scale. If we were to replace our Sun with TON-618's black hole, its event horizon would extend far beyond the orbit of Pluto, engulfing our entire solar system and reaching nearly 1 light day in diameter. This comparison helps illustrate the black hole's enormous size in a context more familiar to most people. Some scientists also use Earth-based analogies to convey TON-618's magnitude. If our planet was scaled down to the size of a grain of sand, TON-618's black hole would be roughly the size of Mount Everest. This stark contrast between the familiar and the cosmic emphasizes the black hole's incredible scale. These analogies serve as mental stepping stones, allowing us to begin comprehending the truly mind-boggling dimensions of TON-618. They bridge the gap between our everyday experiences and the extreme scales encountered in the universe, making the concept more accessible to the public. TON-618 is often featured in documentaries as one of the most extreme objects in the known universe. Presenters typically introduce it as an ultra-massive black hole, emphasizing its staggering size and mass. They explain that it lies at the heart of a distant quasar, an incredibly bright cosmic object powered by the intense energies of matter falling into the black hole. Documentaries usually highlight the fact that TON-618 is estimated to be about 66 billion times more massive than our Sun. This comparison helps viewers grasp the enormous scale of the black hole. They might also mention that its event horizon, the boundary beyond which nothing can escape its gravitational pull, is larger than our entire solar system. To put its size into perspective, documentaries often compare TON-618 to the supermassive black hole at the center of our Milky Way galaxy, Sagittarius, a star. They point out that TON-618 is over 10,000 times more massive than Sagittarius, a star, which itself is already millions of times more massive than our Sun. Documentaries frequently discuss the mysteries surrounding the formation of such an enormous black hole. They might explore theories about how these ultra-massive objects could have grown so large so quickly in the early universe, and what their existence tells us about cosmic evolution and the nature of galaxies. The discussion of TON-618, an ultra-massive black hole, brings several ethical considerations to the forefront. First and foremost, we must address the responsibility of scientists and educators to accurately convey information about cosmic phenomena without causing undue alarm. TON-618, while an extraordinary object, is located billions of light-years away from Earth and poses no direct threat to our planet or solar system. However, the sheer scale of TON-618, estimated to be 66 billion times the mass of our Sun, can be overwhelming to contemplate. This raises questions about how to present such information in a way that inspires awe and curiosity rather than fear or existential dread. It is crucial to balance the presentation of facts with context, helping viewers understand the vast distances involved and the current limitations of our ability to interact with or be affected by such distant objects. Another ethical consideration is the potential misuse or misinterpretation of information about TON-618 and similar cosmic phenomena. In an age of misinformation, There is a risk that discussions of powerful cosmic objects could be taken out of context or used to support pseudoscientific claims or conspiracy theories. Scientists and educators have a responsibility to present information in a clear, factual manner that leaves little room for misinterpretation. Lastly, we must consider the broader implications of studying objects like TON-618. While they may seem distant and irrelevant to everyday life, understanding these extreme cosmic environments can provide valuable insights into the fundamental laws of physics and the evolution of the universe. Ethically, we must weigh the importance of pursuing this knowledge against other pressing scientific and societal needs, ensuring that our cosmic explorations contribute meaningfully to human understanding and progress. TON-618, the most massive known black hole in the observable universe, has sparked profound philosophical discussions about the nature of cosmic extremes and our place within the vast expanse of space. This supermassive giant, with a mass equivalent to 66 billion suns, challenges our understanding of how such enormous structures can form and exist. The sheer scale of TON-618 prompts us to reconsider our concepts of size and mass in the cosmos. It raises questions about the limits of growth for celestial objects and whether there might be even larger black holes beyond our current observational capabilities. This speculation leads to deeper inquiries about the fundamental laws governing our universe and whether they remain consistent across all scales. Furthermore, TON-618 fuels debates about the role of supermassive black holes in galactic evolution. Scientists ponder whether these cosmic giants are the primary drivers of galaxy formation, or if they are a byproduct of other cosmic processes. This line of questioning extends to broader philosophical discussions about cause and effect in the universe and the interconnectedness of cosmic phenomena. The existence of such an enormous black hole also prompts reflection on the concept of time. Given that light takes billions of years to reach us from TON-618, we are essentially observing the distant past. This realization sparks contemplation about the nature of time itself and our perception of cosmic history, leading to profound questions about the past, present, and future of our universe. TON-618 serves as a prime example of the unfathomable scale and power of the universe, making it a compelling subject for cosmic horror narratives. This ultra-massive black hole, located billions of light-years from Earth, is one of the largest known black holes in the observable universe. Its sheer size and gravitational influence challenge our understanding of physics and the formation of cosmic structures. In literature and film, TON-618 represents the kind of celestial object that embodies the core themes of cosmic horror, the insignificance of humanity in the face of vast, incomprehensible cosmic forces. Its enormous mass, estimated to be 66 billion times that of our Sun, creates a sense of awe and terror that aligns perfectly with the genre's focus on the unknown and unknowable aspects of the universe. Writers and filmmakers often use TON-618 as a backdrop for stories that explore the psychological impact of confronting such immense cosmic entities. The black hole's existence raises questions about the nature of reality, the limits of human perception, and our place in the universe. These themes resonate strongly with the existential dread that characterizes cosmic horror. Moreover, TON-618 serves as a reminder of the potential dangers lurking in the cosmos, fueling speculative narratives about the consequences of encountering such massive objects. Its presence in cosmic horror stories often symbolizes the ultimate abyss, a void that can swallow not just matter and light, but entire civilizations and even reality itself. TON-618, the ultramassive black hole at the heart of a distant quasar, is expected to remain active for an incredibly long time. This cosmic giant, with a mass estimated at 66 billion times that of our Sun, has an enormous appetite for matter. As it continues to devour surrounding gas, dust, and stars, it will sustain its intense activity for millions, if not billions, of years to come. The lifespan of such an active galactic nucleus depends on the availability of material to fuel it. Given the immense gravitational pull of TON-618, it can draw in matter from vast distances, ensuring a steady supply of cosmic fuel. This process is self-sustaining to a degree, as the intense radiation and jets produced by the feeding black hole can trigger star formation in its host galaxy, creating new sources of future sustenance. However, even this cosmic behemoth cannot feed indefinitely. Eventually, as it consumes the available matter in its vicinity, its activity will begin to wane. This process could take billions of years, potentially outlasting many of the stars in its host galaxy. The exact timeline remains uncertain, as our understanding of such extreme objects continues to evolve with new observations and models. What we can say with confidence is that TON-618 will remain an object of intense scientific interest and study for generations of astronomers to come, offering insights into the nature of supermassive black holes and the evolution of galaxies in the early universe. TON-618, the most massive known black hole in the observable universe, presents a fascinating case study in cosmic extremes. As this supermassive black hole continues to consume matter from its surroundings, its growth will have profound effects on its host galaxy and beyond. The immense gravitational pull of TON-618 will draw in more gas, dust, and even stars from its vicinity. This process will lead to increased activity in the galactic core, potentially triggering bursts of intense radiation and powerful jets of particles shooting out from the black hole's poles. These energetic outbursts could influence star formation rates in the host galaxy, possibly suppressing new star birth in some regions while stimulating it in others. As TON-618 grows, it will exert an ever stronger influence on the structure of its host galaxy. The increased mass at the center could alter the galaxy's rotation curve and affect the orbits of stars and gas clouds throughout the system. This might lead to a redistribution of matter within the galaxy, potentially changing its overall shape and dynamics over extremely long timescales. The growth of TON-618 also raises intriguing questions about the limits of black hole size. Some theories suggest there might be an upper limit to how massive a black hole can become before its growth slows significantly. Whether TON-618 will approach such a theoretical limit remains an open question, one that continues to challenge our understanding of these cosmic giants and their role in galactic evolution. TON-618, the most massive known black hole in the observable universe, exerts an immense influence on its surroundings. This colossal supermassive black hole, with a mass equivalent to 66 billion suns, resides at the heart of a quasar more than 10 billion light-years away from Earth. As TON-618 continues to grow and evolve over cosmic timescales, it will dramatically shape the structure and destiny of its host galaxy. The immense gravitational pull of this behemoth will likely draw in vast amounts of gas, dust, and even entire star systems from the surrounding galactic regions. This process of consumption will lead to a gradual depletion of material in the galaxy's outer regions, potentially resulting in a more compact and elliptical galactic structure over time. The intense radiation and powerful jets emanating from the accretion disk around TON-618 will also play a crucial role in galactic evolution. These energetic outflows can heat up and expel gas from the galaxy, effectively shutting down star formation in certain regions. This phenomenon, known as quasar feedback, could lead to the premature aging of the galaxy, transforming it into a massive elliptical galaxy dominated by older, redder stars. Furthermore, the sheer gravitational dominance of TON-618 might influence the orbits of stars and gas clouds throughout the galaxy, potentially disrupting spiral arm structures and altering the overall distribution of matter. In the most extreme scenarios, TON-618 could even consume a significant portion of its host galaxy's mass, leaving behind a relatively bare galactic core surrounded by a vast, diffuse halo of stars and gas. TON-618, a supermassive black hole of staggering proportions, resides at the heart of a distant quasar. Its immense gravitational influence certainly raises questions about its potential impact on surrounding cosmic structures. However, the threat it poses to other galaxies is minimal due to its vast distance from our own Milky Way and other nearby galactic systems. The enormous size of TON-618, estimated to be about 66 billion times the mass of our Sun, does give it a gravitational reach that extends far beyond its host galaxy. This powerful pull affects the movement and distribution of stars, gas, and dust within its vicinity. Nevertheless, the vast expanses of intergalactic space serve as a buffer, preventing direct interactions with most other galaxies. In the grand cosmic dance, galaxies do occasionally collide and merge, a process influenced by the gravitational forces of their central black holes. However, these events occur over billions of years and are driven more by the overall mass distribution of galaxies rather than individual black holes, even ones as massive as TON-618. While TON-618 itself may not pose an immediate threat to other galaxies, studying such extreme objects helps scientists better understand the role of supermassive black holes in galactic evolution and the large-scale structure of the universe. These insights contribute to our knowledge of how galaxies form, interact, and change over cosmic timescales. The eventual death of TON-618, one of the most massive black holes ever discovered, will be a cosmic event of unimaginable scale. This supermassive black hole residing at the center of a distant quasar will likely meet its end through a process called evaporation, albeit over an incomprehensibly long timescale. As with all black holes, TON-618 emits a form of radiation known as Hawking radiation. This phenomenon, predicted by Stephen Hawking, causes black holes to lose mass over time. For a black hole as enormous as TON-618, this process is currently negligible. However, over vast eons, as the universe continues to expand and cool, this radiation will become the dominant factor in the black hole's evolution. The evaporation process will accelerate as the black hole shrinks, with the final moments occurring in a burst of high-energy radiation. However, given the sheer mass of TON-618, estimated at 66 billion times that of our Sun, this process would take an almost inconceivable amount of time, far longer than the current age of the universe. Before its final demise, TON-618 might also consume all available matter in its vicinity, entering a dormant phase where it no longer actively accretes material. In this state, it would become a silent behemoth, gradually losing mass through Hawking radiation until its eventual evaporation. TON-618, the most massive known black hole in the observable universe, will play a significant role in shaping the cosmic landscape far into the future. As this supermassive giant continues to consume nearby matter and merge with other black holes, it will grow even more enormous over billions of years. In the distant future, as galaxies collide and combine, TON-618 is likely to become the central black hole of a massive galaxy cluster. Its immense gravitational influence will affect the motion and evolution of countless stars and planets within its expanding domain. As the universe continues to expand and cool, TON-618 will remain an island of intense activity. Long after star formation has ceased in most of the universe, this behemoth will continue to emit energy through Hawking radiation, albeit at an extremely slow rate due to its enormous size. Ultimately, in the far distant future of the universe, when most other structures have decayed, TON-618 may be one of the last remaining organized systems, slowly evaporating over unimaginable timescales and serving as a final bastion of concentrated energy in an otherwise empty cosmos. As the universe continues its relentless expansion, the fate of TON-618, the most massive known black hole, becomes an intriguing subject of speculation. This cosmic behemoth, with a mass equivalent to 66 billion suns, will likely undergo several changes over the immense timescales of cosmic evolution. One significant effect of the expanding universe on TON-618 will be its increasing isolation. As space stretches, the distances between galaxies grow, potentially leaving this supermassive black hole in a cosmos that becomes progressively emptier. This isolation could impact the black hole's ability to consume nearby matter, potentially slowing its growth rate over time. Despite the universe's expansion, TON-618 will continue to exert its powerful gravitational influence on its immediate surroundings. It may continue to draw in nearby stars and gas, maintaining its status as an active galactic nucleus for billions of years to come. However, as the universe ages and star formation rates decline, the supply of new material for TON-618 to consume may gradually diminish. The expansion of the universe also raises questions about the long-term fate of such massive black holes. Some theories suggest that in the far distant future, even these giants might evaporate through Hawking radiation, a process that would take an almost unimaginable amount of time for an object as massive as TON-618. However, this process would only become significant when the universe has aged far beyond its current state. The collision of two supermassive black holes like TON-618 would be an extraordinary cosmic event, releasing enormous amounts of energy and reshaping the fabric of space-time itself. As these behemoths spiraled towards each other, they would create powerful gravitational waves, ripples in the cosmos that would spread across vast distances. The merger would unleash an astonishing amount of energy, briefly outshining entire galaxies. This cosmic dance would distort the space around them, potentially ejecting nearby stars and gas clouds at incredible speeds. The intense gravitational forces could even trigger bursts of star formation in surrounding regions. The result of this titanic collision would be a single, even more massive black hole. This new cosmic giant would have a significantly larger event horizon, the boundary beyond which nothing can escape its gravitational pull. The merger would also likely produce a quasar, an extremely bright galactic core powered by the intense heat and energy of matter falling into the newly formed black hole. Such an event would provide astronomers with a unique opportunity to study the behavior of space, time, and matter under extreme conditions. The gravitational waves produced would offer valuable insights into the nature of gravity and the structure of the universe, furthering our understanding of these cosmic titans and the fundamental laws that govern our reality. TON-618, a supermassive black hole of staggering proportions, exerts an enormous influence on its cosmic neighborhood. This behemoth, with a mass estimated at 66 billion times that of our Sun, resides at the heart of a distant quasar. Its gravitational pull is so intense that it dramatically shapes the destiny of its entire local group of galaxies. The immense gravity of TON-618 acts like a cosmic vacuum, drawing in vast amounts of matter from its surroundings. This process accelerates over time, potentially leading to the merger of multiple galaxies within its sphere of influence. As these galaxies are pulled closer, they may be torn apart, their stars and gas becoming fuel for the insatiable appetite of the supermassive black hole. This ongoing consumption could result in TON-618 growing even more massive, further amplifying its gravitational dominance. Over billions of years, this process might lead to the formation of a single, enormous elliptical galaxy centered around the supermassive black hole. The local group's original structure would be completely transformed, with most of its matter either consumed by the black hole or redistributed into this new galactic giant. However, the influence of TON-618 extends beyond mere consumption. Its powerful gravitational effects could also alter the trajectories of stars and gas clouds throughout the local group, potentially triggering new episodes of star formation in regions where this material becomes compressed. This dual role of destruction and creation showcases the complex and far-reaching impact of such an extraordinary cosmic object on its galactic neighborhood. TON-618, the most massive known black hole in the observable universe, offers us a fascinating glimpse into the potential future of cosmic structures. This supermassive giant, with a mass equivalent to 66 billion suns, challenges our understanding of black hole formation and growth. The existence of TON-618 suggests that the universe can produce truly enormous cosmic structures far beyond what we once thought possible. This implies that over extremely long timescales, the gravitational influence of such massive objects could significantly shape the evolution of galaxies and galactic clusters. As we look towards the distant future of the universe, objects like TON-618 might play a crucial role in determining cosmic structure. These supermassive black holes could continue to grow by merging with other black holes and consuming surrounding matter, potentially becoming even more dominant features of the cosmos. However, TON-618 also raises questions about the limits of black hole growth. Its immense size prompts us to consider whether there is an upper limit to how large these cosmic behemoths can become, and what factors might constrain their growth over the lifespan of the universe. By studying TON-618 and other extremely massive black holes, we gain valuable insights into the long-term fate of matter and energy in our universe.